Światło to jest niesamowite zjawisko. To jest podstawowy składnik materii całego wszechświata, który tak naprawdę spaja wszystkie atomy, molekuły, wszystko co znamy. Światło definiuje czas i przestrzeń. Jest zupełnie niesamowitym czynnikiem, który my jako ludzie możemy odbierać bezpośrednio za pomocą naszego wzroku. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. W tym właśnie zajmuję się ja i mój zespół, próbując oswoić światło i zastosować je do czegoś praktycznego.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin, więc z łatwością zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Wszyscy moi znajomi uważają mnie za pewnego rodzaju magika i poniekąd jest to prawda, bo w tej pracy łączymy różne elementy takiej zaawansowanej techniki optycznej, wyrafinowanej obróbki danych, do tego szczypta inżynierii, żeby tworzyć urządzenia, które poniekąd są magiczne, bo pomagają diagnozować choroby różnego rodzaju, które normalnie nie są widoczne gołym okiem.
Nauka obok sztuki jest jednym z najważniejszych aspektów działalności człowieka. Sztuka może leczyć duszę, ale nauka może leczyć ciało. My zaczynamy od oka.
Lasery, modulatory, mikroskopy i inne urządzenia to jest dla mnie fascynująca zabawa. Eksperymenty naukowe, mimo że często są bardzo zaawansowane, są do ogarnięcia przez jednego człowieka. Teraz pracuję nad taką zaawansowaną techniką obrazowania ludzkiego oka. Mam nadzieję, że ta technika będzie kiedyś stosowana przez lekarzy, wspomagając wczesne wykrywanie różnych schorzeń wokół i będzie techniką nieinwazyjną, to znaczy jak najbardziej bezpieczną dla pacjentów.
I like building microscopes, but as any other instrument, it has its own limitations. So my job is to improve the performance of a microscope. This also means that what I'm doing day to day hasn't been attempted before, which could sometimes be challenging, but always exciting.
My dreams are to finish my project, which is really very challenging, to study about the small growth of the tumors and do something to understand the basic biological and physical process beyond this, to understand how they're really developing and have like a good pharmaceutical drug to cure it.
Pracuję nad nowymi metodami obrazowania, które zrewolucjonizują te metody, które mamy obecnie w mikroskopii, czy też generalnie w kamerach.
Fajnie współpracować z ludźmi, dla których rzeczy niemożliwe nie istnieją. Myślę, że najlepsze słowa opisujące pracę u nas w zespole to mierz wysoko i sięgaj celu.
My research aims to better understand how human eyes work. To me, being a scientist is having the opportunity and the duty at the same time of learning something new every day.
W naszych projektach cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki pod skórą, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Ladies and gentlemen, I have a pleasure to welcome you to i-POB conference on behalf of the Scientific and Organizational Committee of this event. This conference is actually it summarizes the European project ERA-CHAIR with acronym CREATE and is fully subsidized from this project. So today we are meeting online. As you can see from the growing number of coronavirus outbreaks in Europe, especially in Poland, this decision seems to be the right one. The positive side of that is that we have a much broader audience now that cover the entire globe. So we are hoping that these inspirational talks that we have in next 2 days will be available for many more people. So a minute ago you had chance to see a movie presenting my group that was started 4 years ago here in Warsaw. So I was invited to this project ERA-CHAIR in the hope of broadening the research area, research scope of research activity of the Institute of Physical Chemistry of Polish Academy of Science. And we, as the acronym stands for CREATE, me and my team, we are focusing on creating new things, creating new instruments, creating new methods, creating new knowledge, but also creating new expertise, creating new facilities, and creating also the reality. So to create reality, we can do so by having impact on it, on our everyday lives. So we were able to 5 groups and continue our work on imaging along with work on introducing new therapies for eye diseases. And at this point, I should thank people who enabled us to expand and they were introducing us to this institute, so especially Professor Robert Hołist, coordinator of ERA-CHAIR CREATE project, and Agnieszka Tadżak and her team, who gave us the full freedom of operation here. And also directors of institute, Marcin Opało, Jacek Gregorowicz, Marek Tkacz, Tadeusz Pacholik, and Adam Kubas, for their support and great trust that they placed in me. And also the entire community of Institute of Physical Chemistry for very warm welcome and a lot of trust. So, but to be honest, I wouldn't be able to achieve anything without constant inspiration that comes from group leaders, scientists, and entrepreneurs from all over the world that are able to really influence the reality and change it. So that is why we decided, me and my colleagues from the scientific committee, Professor Krzysztof Gorecki, Professor Małgorzata Kujawińska, and Chris Palczewski, to share these experiences and show how others, how to think, plan, and implement their research actions to have results that can be immediately materialized. So I wanted really the best of the best to talk about their experiences. And that's why we decided to organize this i-POB conference and invite many wonderful and outstanding people who are happy to share their experiences. All the presenters that will show their papers, their talks, are from the group that were very successful in implementing their own solutions and developing new technologies. So for the next 24 hours, we'll hear 17 fantastic talks, absolutely
absolutely exceptional talks and unique about these experiences. And I hope that for all of us, it will be a huge, it will have huge impact on our actions, and we will be able to use our time more efficiently. Because every morning I'm waking up and I have this feeling that time runs out faster and faster. So with this, I would like to start and he is also Chief Scientific Officer at Oncores Medical. So Brendan expertises in oncologic optical elastography, and he's really inventor of this field. So he pushed this field forward very much. And Brendan will share with us his experience about the academia and as a PI and as the industrial with his industrial partnership. So let's start Brendan talk.
Thank you very much, Maciej. It's very nice to see you, and thank you very much for the invitation. It would have been much nicer, of course, to visit Poland, but this is a close second. So in this talk, I'll describe the work that we've been doing in the lab in collaboration with Oncores Medical to develop this elastography technique based on OCT for an application in cancer surgery. So it was fascinating to look at Jan's talk and to see the developments that they've undertaken in the last number of years. Oncores are at a much earlier stage. We just actually moved into our own office outside of the Medical Research Institute in the last month or so. And so really Oncores is at this stage of product development and the clinical validation to support FDA applications. In this talk, I'll mainly focus on the technology and the clinical studies, but happy to answer any questions more specifically about commercialization. And I'll try to add some details as we go through the talk as well. So the next slide, please. Thank you. So so the background of the talk, I'll first of all describe the technique that we've developed, which we call quantitative microelastography. I'll then talk about a clinical study that we've performed to really when the company formed, the biggest question that the investors had was around the diagnostic accuracy. So we really focused on trying to prove in a benchtop scenario initially what the sensitivity and specificity of the technique is. We're now moving forward to, we've begun an in vivo study with a handheld probe where we're scanning residual cancer in the patient, but I won't talk about that too much today. I'll instead also talk about some new IP that we've developed in a technique to make a more practical surgical device. So I think we've learned as we've, OCT is a relatively complex imaging system. It's pretty expensive as well, which is always an issue when you're trying to translate a technology into a clinical scenario. So we've been thinking about ways that we could maybe retain most of the information provided by OCT elastography, but in a format and a form factor that's much more cost effective and suitable for use in surgical devices. So I'll touch on that as well. Next slide, please. So optical coherence elastography, the kind of generic OCT-based elastography technique, it's really in common with ultrasound and MRI-based versions of elastography. It's a technique or a set of techniques to image the mechanical properties of tissue, as they're often associated with disease. The advantage of OCT or optics in general over ultrasound and MRI is, of course, resolution. But with that limited penetration depth. So unlike, say, ultrasound elastography, which has found many diverse applications, I think the limited penetration depth of OCE makes it quite a niche application for specific scenarios. One of those scenarios we believe is in to aid surgeons in resecting tumors, because the penetration depth is not an issue there when you've got an open surgical field. So that's the application we've been pursuing most heavily. And just to give you a sense of the different type of scales that we can see with OCE versus what they see with ultrasound elastography, it shows two images here of the human breast. recorded with those different imaging techniques. Next slide, please. So the generic steps in OCE are to apply some form of mechanical load to the tissue. We then image the deformation with OCT, phase-sensitive OCT, typically before and after the deformation has been applied. And we then input the measured displacement or deformation to a mechanical model of the tissue, and that allows us to map at each pixel in the image a mechanical property of interest, and in our case that's elasticity. Next slide, please. So there are a number of different ways to do OCE, and it kind of really depends on what your application is, and they can be classified based on the way that you apply that mechanical load. So the way we do it is similar to a compression test with an imaging function called compression OCE. Other techniques, for example, Kira Laren's group and Ricky Wang's group in the US, they're focused more on ophthalmic applications where contact with the eye is more complicated. So they've looked more at non-contact versions of OCE to create, for example, propagating shear waves in the tissue that allows them to quantify elasticity. But in our application in breast cancer, the contact is not an issue. And importantly, so we apply a deformation of about typically around 10% kind of bulk strain on the tissue. And we then use a PZT actuator to impart a smaller scale deformation to the tissue that can be detected with phase-sensitive OCT. The reason we feel compression is really important in the surgical scenarios is that simple mechanical load that you apply actually makes it much more amenable to making handheld imaging probes and compact probes, but also for rapid acquisition. Although the deformation is at a lower rate, it gives you the opportunity to capture that deformation in a volumetric manner, in a faster manner than you can with the wave-based approaches, which typically require some measurement of the deformation as a function of time to capture a few cycles of the wave. Next. So this is just a slide to describe how the assumptions we make in order to measure elasticity. So from a mechanical engineering perspective, elasticity is stress divided by strain, so the force per unit area applied to the tissue divided by the deformation imparted to the tissue. But that's really described by a fourth order tensor. So you've got these stress and strain tensors, which give you effectively 81 elasticity constants. So very early on in ultrasound elastography in particular, they recognized that they needed to make some assumptions in order to reduce these 81 elastic constants to one elastic constant that could be easily represented in an image that's required for elastography. So the assumptions that are made typically, and that we make as well, are that the tissue is linear elastic, isotropic, and incompressible. And in our case also, we're only measuring the axial deformation. So that reduces this fourth order tensor to a simple scalar effectively, where we're measuring the axial stress divided by the axial strain to measure elasticity. Now, of course, those assumptions come with caveats, and they can impact the accuracy of the measurement in various scenarios. So outside of I think one of the advantages that we've had with Oncores Medical and the collaboration with the lab is that we've been able to stay on the main track of the company, which has to be focused on measuring on the clinical application and product development. There's not really the time and money to kind of get sidetracked. But what we do is make opportunities to take some of these more research questions about, for example, how accurate is the technique in spite of these assumptions. And so, as illustrated in these papers, for example, at the bottom of the slide, we've been looking at those in a more research context to establish the limitations. And what that work has shown is that once the kind of paradoxically, once the contrast between different regions of tissue from a mechanical perspective is not too large, then the assumptions that we make are not too bad. And that stands to reason, because at the end of the day, we're assuming that the tissue is linear elastic and uniformly elastic. So the closer we are to that approximation, the closer our measurements will be. Next slide. So first of all, we measure the axial strain. So I'll just describe briefly how we do that. So as I mentioned, we use a PZT actuator, and we impart a deformation between two OCT B scans. Looking at the phase of those B scans, as many of you will know, the phase of an OCT image is temporally invariant. So if we apply a deformation, if that deformation is not too large, we're able to track the variations in the phase, or the difference between the phase between the two images at different deformations, to measure the displacement at each point in the B scan. We can then relate that to the displacement we measure to strain by measuring the gradient of the displacement as a function of depth. So this is really the terminology we use is to call this a local strain measurement. So we're picking out how the sample deforms differently at different points throughout its depth. One important point is that all elastography techniques require a degradation in resolution, and we need to sacrifice axial resolution to measure this strain because we're measuring it over a fixed depth. Typically, that axial strain is measured in about 50 to 100 microns, but that gives us these type of elastograms that we see here, where in this case it's a silicone phantom with a stiff inclusion, and you can see that the stiff inclusion doesn't deform, it's just translated within the softer surrounding silicone. So that gives us this low strain signal and enables us to pick out different mechanical features. Next. So, of course, with OCT, we can do that in 3D as well. So one of the early demonstrations that we had kind of when we were just starting some of our clinical work was to kind of contrive a phantom where we had strong mechanical contrast, but we didn't have much OCT contrast. So we matched the optical scattering properties of the stiff inclusion with the surrounding material, and we can see that we can pick out quite nicely the place where these stiff inclusions are located. So that gave us confidence to move forward, and if we can go to the next slide as well. But the problem with that, of course, is that we're only measuring the strain. But as I mentioned, elasticity is the stress divided by the strain. And this problem manifested pretty early when we went to the clinic, in that the pathologist would give us a sample of human breast tissue that had kind of like a column of tumor beside a softer surrounding fat tissue, for example. But when we applied our compression plate across the surface, we weren't able to deform the softer material because the load was taken fully taken by the stiffer material. So from a practical reason, we needed to figure out a way around this, but also from a clinical point of view, it's very important to be able to quantify the variable that you're measuring so that you can look between patients to try and figure out what constitutes cancer and not. So our approach to measuring stress was well, first of all, we thought maybe we can just apply a load cell, which is the most typical way to measure force. But this wouldn't give us the pixel by pixel measurement of stress that we really needed to kind of relate to our strain measurement. So instead of that, what we did was actually take the silicone material that we use as phantoms. So importantly, it's around the same stiffness as breast tissue. And we placed that between the imaging window, which is attached to the PZT actuator. So it's applying the mechanical load. We put the silicone between this imaging window and the sample. And what happens then is, as you deform the silicone on top of the sample, any variations in mechanical stiffness beneath the layer will lead to greater or lesser deformation of the layer. As we see in the OCT image here, we have this increased deformation above the stiff inclusion. Of course, from that we can easily measure strain, but what we're after is stress. But importantly, because we made this material, we can characterize its stress-strain relationship before we perform the elastography imaging. And that allows us to relate the experimentally measured strain to the stress at the surface of the tissue. And that enables us to measure these surface stress maps. Next slide. So now if we go back to our kind of mechanical model, we've got the three-dimensional axial strain. We've got the surface stress. Importantly, we are making the assumption that the stress is uniform with depth. But nonetheless, for a practical surgical imaging probe, this enables us to measure the elasticity as illustrated here. Next slide. So one early demonstration of the kind of contrast we can get is that is shown here. So we have on the left-hand side histology, which we use as a gold standard. This is the imaging that pathologists use to determine if there's cancer present in the specimen or not. We've got the OCT image in the middle, and then we've got our elasticity image or elastogram on the right. So this showed us at this early stage that we could at least in this case, have quite a lot higher contrast between tumor and non-tumorous dense tissue stroma. We had much greater contrast than we could get with OCT. And it was really this type of quite clear contrast coupled with the very large clinical problem that we're trying to address that I think was key to convincing investors to invest in OncoRes. Next slide. And so I'll now talk about the, before that, just to say, beyond the tumor margin technique that I'll describe in the next slide, we're looking at many different applications of this technology, mainly in a research setting, but also increasingly we're looking for new opportunities for new surgical applications, for example, in neurosurgery, that would be enable us to develop a second application for OncoRes. Next slide. So the clinical problem, now that I've described the technology in a bit of detail, I'll describe the clinical problem that we're trying to address. And that problem is in breast conserving surgery. So it's a very big problem. There's more than 2 million cases of breast cancer diagnosed worldwide annually. And importantly, there's two main surgical options that the surgeons can take. The first is mastectomy, which is removal of an entire breast. And the second one is breast conserving surgery, where the aim of the surgeon is to remove the tumor and a rim of healthy tissue surrounding the tumor. Now, importantly for us, with the onset of mammography over the last 20, 30 years in particular, we're detecting lesions in the breast when they're much smaller at an earlier stage. And that's led to this big shift towards breast conserving surgery as opposed to mastectomy. It's now in about 2/3 of breast surgeries in places like the EU or Australia and the US. Breast conserving surgery is elected because it's often deemed as a bit too aggressive to remove an entire breast if it's a smaller lesion in particular. Obviously, there's much less cosmetic outcomes, and it's a much less traumatic surgery for the patient if they have just a lump removed. Importantly, removal of the lump, if it's followed up by post-operative radiotherapy, has the same prognosis for the patient in terms of survival. But the problem with breast conserving surgery is that at the moment when the surgeon is removing the cancer, they don't have any tool to tell them if they've got all of the cancer out or not. So they're relying on their sense of touch or their eyesight to try and guide them if they need to take additional tissue out or not. Not surprisingly, that's very crude. In around 20 to 30% of surgeries, depending on the study, a re-excision is required. That means that following the surgery, the pathologist looks at the sample under the microscope days after the surgery, and they see cancer at the edge of the excised tissue in this 20 to 30% of cases. If that happens, the patient needs to go back for a re-excision surgery. So our goal with this technology is to be able to perform this intraoperatively. So to be able to give the surgeon some feedback. It may be an image, or maybe it's more practical in a surgical scenario to give some audio feedback to the surgeon to indicate that there's a suspicious region. That would enable the surgeon to take an additional slice of tissue to try and ensure that they've got all of the cancer out and that a re-excision is not required. Importantly for us, this is a very widely accepted problem. I mean, the numbers are so large, and the kind of from a commercial point of view, the market is so large that we've really gained a lot of encouragement from surgeons that if this works, they'd really use this technology. Next slide. So yes, we started clinical scanning in around 2012 when the technology was at a much earlier stage. This was when we were just doing strain imaging. But we found that at that stage, from about 2012 to 2015, that's really where we had this very important feedback from the technical developments to the clinical outcome. And for example, that stress measurement technique that I mentioned was really stemmed from this kind of feedback mechanism that's proved really interesting. It was then after that, from 2016, when Oncores Medical was formed, that we started to lock down the protocols of the excised of the specimen imaging technique and move towards more measuring the diagnostic accuracy, as I'll describe now. And then last year we started this in vivo study. So in total, across these studies, we've scanned more than 250 patients in a number of hospitals in Western Australia. All of this work was really enabled by our very close collaboration with Christabel Saunders, who's a very prominent breast surgeon in Australia, and also Bruce Latham, leading pathologist in Western Australia. So again, having Christabel and Bruce involved, that clinical input from a very early point was critical to the development of the technique, but was also really important in kind of pitching our story to investors. I mean, if we were just technology people coming along saying, hey, we can solve this problem, we wouldn't have got anywhere near as far as we have so far. But having Christabel not only as a champion for the technique, but actually being one of the team, I think was really instrumental in the early stages of the company. Next slide. So in this slide and the next slide, I just wanted to show another example of the additional contrast we can get with elastography, and also to highlight that to image the protocol we developed to image our specimens, we wanted to be able to image an entire face of a specimen, an entire margin. And so to do that, we developed this wide field imaging technique. You can see the stitching artifacts here, where we stitch a number of images, OCT on-FOSS images together, in order to give us about a 45 by 45 millimeter on-FOSS field of view. We look at the on-FOSS plane for two reasons, one clinical and one technical. Clinically, you can see a lot more information across that large field of view than you could within one B-scan. And secondly, our axial resolution is degraded because of the measurement of strain, as I mentioned. So we maximize our resolution, and therefore, again, the information we're providing to surgeons in that plane. So again, all the time we co-register with histology, which gives us our ground truth. In this case, in the center of this image, where you can see the arrow pointing to tumor, there's very dense invasive ductal carcinoma, and around the edges, you can see the kind of more pinker stained tissue, which is non-tumorous dense stromal tissues. We can see with OCT that we can pick up the contrast between the adipose and the tumor, and the dense tissue, but we can't really distinguish very clearly what's happening within the dense tissue. When we now overlay, in the next slide, we overlay the elasticity on top of that. We see in this color-coded image that the high stiffness regions, when we sit down with the pathologist and correlate them, they correspond quite accurately to where the tumor was. So we developed all of these protocols on mastectomy specimens, which are not the diagnostic, the clinical use case, as I mentioned. It was easier to access this tissue at the early stage. The pathologist could give us a region of tissue from the central region of the mastectomy that wasn't used for diagnostic purposes, so we could have more time to scan this, etc. Once we locked down the imaging protocol, we then moved forward, next slide, to look at the real clinical use case, which is to assess the sensitivity and specificity on wide local excisions or lumpectomy specimens. These are the specimens that are excised during breast conserving surgery and that often have a tumor at the edges of the margin. So to do this, following surgery, we scanned typically 2 margins in about 50 minutes. So we were just aiming to, from a clinical point of view, could we tell if there was tumor in an image or not? We weren't at a point where we could give feedback to the surgeon that they could act on during the surgery. So for that reason, we took our time. We scanned 2 margins per specimen. We then matched that with histology, as I mentioned. We gave the OCT images and the elastography images to 7 readers, comprising pathologists, surgeons, radiologists, and engineers as well. Of course, blinded to the histology image, they made a decision, and we then corresponded that with the co-registered histology to establish the accuracy of the technique. We had 90 patients in this study. 71 were included in a reader study, and 19 were used to develop the training, the guidelines for surgeons and other readers. Next slide. So just a bit more about the study before I show you some results. We scanned 141 margins in total, so almost 2 in every case. From that, following the precedent that was set by other similar studies, we defined regions of interest, which were volumes over a surface area of 10 by 10 millimeters across a margin with a depth of 1 millimeter. So we gave these volumes together with the guidelines for reading the images to the readers. We excluded a number of regions of interest for various reasons. Sometimes there was no contact made between the tissue and the imaging plate. There was imaging artifacts. There was a particular type of cancer, mucinous ductal carcinoma in situ, which is very rare. And so because we only saw it twice, we didn't have enough information to guide the readers. But some of these exclusion criteria are also important for the future development of the technique. So as well as doing this in the clinical study, it's also spurred a lot of technical development that's ongoing to try and remove some of these issues, so we can make a very robust device going forwards. So about 24 or 15.6% of the scanned regions of interest had cancer in them, and 130 had no cancer. Next slide. So I'll briefly just go over the decision tree. It was quite interesting, actually, from a clinical point of view. We were quite naive when we started this study. So the first decision trees that we made, so these are the decision-making process that we ask readers to go through. At the start, we made it very complex because we wanted to make sure we had every chance of getting it right. But what ended up being, there was about 12 or 15 decisions that the readers had to make. And we quickly realized when we gave this to some of the readers that this wasn't going to work, because they don't have too much time to do this. And also in the clinical use case, there's not going to be too much time to use it. So we stripped the decision trees right back to make them as simple as possible, but still hopefully being able to accurately determine if there's cancer or non-cancer in a given image. OCT is actually used, there's a number of companies developing OCT in its own right as an imaging technique for this application. Because our information for elastography is gathered from OCT, we could use OCT, we could compare our elastography results to OCT directly. And also we had the opportunity to combine OCT with elastography. We expected that the combination of this information would give us a higher sensitivity and specificity. Next. So I'll just now show you on the next 3 slides some of the different images that we've acquired. First of all, I'll show you some negative margins. Negative meaning that there was no cancer at the edge of the specimen, so that's good for the patient. The first case was just adipose tissue or fat. We see in OCT is actually really good at picking out adipose, because it's you've got this very high refractive index change at the cell membrane, the adipose membrane, to the lipids inside. So you see this typical honeycomb structure. So in that case, we developed an algorithm that would identify where adipose tissue was, and we didn't overlay elastography in those regions because we knew that OCT would give us the information. In the denser regions of tissue, such as here in this benign stroma or fibrous tissue, this is where it's really tricky, as I mentioned, for OCT. This is where we overlay the elasticity information. In this case, we see that the elasticity is generally quite low. We've got this, you can just about see on the color bar here in the elasticity images, there's a threshold above which the training data determined that it was likely to be tumor, below it wasn't. So we see that in this case that the elasticity is typically very much below the threshold, and so we would call this a benign region. Next slide. Now I'll show you 2 cases of invasive ductal carcinoma. This is the easiest clinically to detect, because it's often quite a large region of tissue, of tumorous tissue, where the cancer is broken out of the ducts in the breast and is now invading the rest of the breast. So in this case, we see very elevated regions of stiffness in the dense regions, corresponding to where histology tells us the tumor is. Importantly, in these cases, we couldn't have a non-FOSS histology map because we couldn't change the way pathologists typically perform histology, because this is diagnostic tissue. So we developed an algorithm where we could identify that where the cross section was from the OCTP scans, and we then look at put this cross section through the on-FOSS image, so we get this indication of whether it's tumorous or not. Next slide. These were two of the really interesting cases. We saw a number of ductal carcinoma in situ cases that showed that there was elevated stiffness, and this is what surgeons always ask about. Again, because we were very closely working with surgeons from the start, we were really focused on trying to see DCIS, because that's the one they miss a lot, and that's the one they all want to be able to detect. So some imaging techniques are really good at invasive cases, but surgeons aren't so interested in that, because they feel, even if they're not right, they feel that they can pick that out themselves. But we see here that we again see this elevated elasticity in the region of DCIS, and also in a relatively rare form of cancer called mucinous carcinoma, where you've got tumor cells floating in mucin. We actually saw elevated stiffness there, and the reason is that the mucin is kind of trapped fluid. So when we compress that, the fluid has nowhere to go, so it gives us an elevated elasticity in our images, which was compatible with the decision tree and actually enabled us to detect cancer. Next slide. So the results of the study I show here, and highlighted in red the key results, that OCT alone, first of all, gave averaged across all of the readers, gave a sensitivity. So sensitivity is really indicating if we say it's cancer, how often are we right? As opposed to specificity, which is if we say it's not cancer, how often are we right?
Okay.
So,
sorry, Brendan, but we
time.
exceeded the time, and sorry for this brute force action.
That's
but,
okay.
The online conferences have own, rules, and we must unfortunately break this. So maybe you can just conclude, and we have to move to another speaker. Sorry for that.
No problem, and it's my own fault, Maciej. I should have taken time. So so just to conclude, the sensitivity of and specificity of elastography was 93 and 96%, so far higher than 69 and 79 that we got with OCT. So that's rather pleasing. So great, yeah. So
okay.
Thank you again, Maciej.
Thank you very much. Thank you, Brendan, for being with us and for your amazing work. So this is really, as you remember, 10 years ago, I was really much more skeptical, but fortunately you haven't listened to me, so that's very good for all of us. So
maybe because I listened to you, Maciej.
Yeah, it's very nice work. So please stay with us on chat, and there are a couple of questions that you can answer offline. Thank you very much, Brendan. Thank you.
No worries. Thank you, Maciej.
Bye-bye.
Thank you.
Okay, our next speaker is Robert Huber. So Robert is now head of Institute of Biomedical Optics and leader of Biomedical Optics Imaging Group at the University in Lübeck. And he's inventor of FDML system, and really he boosted the field of megahertz OCT technology. So Robert, internet is yours, so please, you can start.
So can you hear me?
Yes, we can hear you.
Okay, fine, because there were some problems before. Good. Maybe just about Brendan, why he was late. I think it's a little bit slower if you do the live with next slide instructions and cannot click on your own. So I think all the speakers are it's not their fault if they are too slow. Good. So I want to talk a little bit about what we call 4D megahertz OCT. So 4D means our systems are now fast enough to really acquire full OCT volumes at video rate and can display them. A lot of applications that we showed previously, and the newest one is this 4D megahertz OCT, where we actually tried to implement this fast OCT and visualizes in augmented reality or mixed reality for surgical microscopes of the future. Next slide, please. Okay, so 4D domain mode locking, the FDML laser was a laser that was actually developed for OCT back then, like in 2003 or 4, when there was the technology transition from time domain to spectral domain, but also to swept source OCT systems. Next slide, please. So we are talking about OCT, and on OCT we always want to measure the echo delay time of light, and there are different versions how you can do this. I think most widely applied is spectrometers with a fast line scan camera. However, you can also do this with a very rapidly narrowband wavelength swept lasers. And when you sweep it once over a range of, let's say, 100 nanometers and detect the interference signal, you can process it similar to spectrometer-based systems and get one line for every sweep. So this means we need to do fast OCT. We need very fast wavelength swept lasers. Next slide, please. So a wavelength swept laser is usually always constructed of a broadband gain medium, and then the resonator provides feedback, and to make it wavelength tunable, there is an optical bandpass filter in it. And as you tune the bandpass filter always to new position, next slide, please. Lasing has to build up at each wavelength from scratch. So you start from fluorescence, then light circulates in the cavity, and just when you have happy lasing, you move your bandpass filter to the next position. And that, of course, inherently limits the maximum achievable sweep speed that you can do, because you always have to wait long enough until you have stable lasing. So one solution is, next, to make the cavity much shorter. And this is what the company Axon Technologies did. And they are, I think, still like market leader on swept sources for OCT. They just made the cavity shorter, so you have more round trips per second. And with this technique, next, they achieved something like 100,000, or I think now 200,000 sweeps per second. And then you still have the end that you cannot like sweep faster anymore. Next. So our approach was to do exactly the opposite, to actually make the cavity much, much longer, that we can now synchronize the optical round trip time with the filter sweep operation. So this means certain wavelength is transmitted through the bandpass filter and now requires such a long time to circulate in the cavity that meanwhile we can sweep the filter one entire cycle, and just when the light comes back and arrives at the filter is there but for the next sweep. And that's true then for all different wavelengths. So we can sweep virtually at any rate. Of course, however, we have to build a cavity that's kind of made for one frequency or the harmonics thereof. Next. So this is the concept how it looks like. Our bandpass filter is a microfiber Perot filter indicated in the top. So you see these two surfaces that go forward, backward. It has a gap of only 1.5 micrometers. So the free spectral range is large enough that you only have one transmission maximum in it. And then you see this blinking triangle, this amplifier, that's a semiconductor optic amplifier. And with this, we can actually realize a very short duty cycle. So you see actually the circulating rainbow only fills up like a quarter of the whole ring. And with this short duty cycle, we can then in passive multiplication stages, so-called buffering stages, multiply the sweep rate and fill up the gaps in between, and then kind of double, quadruple, or like multiply it by 8, increase the effective sweep rate. So with the filter sweep drive frequency of 400 kilohertz, we can go routinely up to 3 megahertz. Center wavelengths, this example like 1300 nanometers, sweep range maybe like 140. We can also build these sources at 1050 nanometers and at 1550 nanometers. Limit is loss of the fiber and dispersion. Next slide. So there are actually now other ways how you can also achieve megahertz OCT speed. So FDML is not the only one. It was the first one and might still have like the best quality image, but there are alternative approaches. One is shown on the top. So it's you use a femtosecond pulse that's spectrally wide, put it through a dispersive fiber, and so it's kind of stretched. And a stretched pulse is nothing else than a wavelength sweep. You can achieve multi-megahertz rates, maybe 80 megahertz, so it's more difficult actually to make slower sources. What's a little bit of problem is the power is kind of low and they are not commercially available yet. Recently, there has been another approach from the Wellman group. It's kind of a mix between FTML and the stretch concept. So they have in the cavity, they compress the pulse, modulate, stretch it, couple it out, and again, so they have then higher power and can achieve 9 megahertz or 18 megahertz or so. Another very promising approach is a short tunable VCSEL laser. So it's extremely short. It's only tuned by moving one side, one mirror, like a membrane in the cavity. Here it's actually not because it's only so short, but you can actually show that the Doppler shift of the light on the moving mirror always fits the new cavity length. And so you have kind of an inherent shifting of the wavelengths. So that gives also very nice performance. It's a little bit old slide. So I think now for the last 2 years, they are commercially available at 400. And I think they are announced at 800 nanometers. 800 kilohertz. So they are getting faster, and maybe sometime they also will achieve the megahertz. I think there have been some lab demonstration by research group who showed already a megahertz. So there will be more sources who in the future will also be able to do megahertz or high quality megahertz imaging. Next. Okay, about megahertz OCT. First, I want to show some previous applications that we already showed, and then this newest one. Next. Before we look into this, let's compare a little bit what actually megahertz speed means. So the first OCT, next, ran at 400 lines per second, the size Stratus OCT time domain. Then next, there were the commercial ophthalmic systems running about 50 kilohertz. And so this slide is only for retinal imaging system. It's about status 2012, but not too much has changed. Next, there was Topcon system at 100 kilohertz next, and they actually advertised it was fastest OCT back then. Now I think there are commercial systems at on the order of 70, 80 kilohertz for ophthalmic. Then there have been research groups, so you can use this axon source that I showed and apply this buffering concept that we demonstrated by multiplying. So they achieve 200 kilohertz. I think now it's 400 kilohertz. Next. Then you can have a fast spectrometer. They are right now, I think, at 600 kilohertz. And then next, MIT group Fujimoto showed something like 600 kilohertz with the VCSEL approach. Next, and with the FTML, actually, we could show this 6.7 megahertz already there in 2012. And what you see, this is not just like a little bit incremental increase. So with this, you really can do things that are not possible at the couple of hundred kilohertz. And this is actually what we want to investigate. We are convinced that not every application needs the high speed, but clearly there are some where the high speed is highly beneficial, if not mandatory. Next. So the first example is ophthalmic imaging of the retina. And here you would see a typical area that OCT system covers, like 20 times 20 degrees on the background of the eye. And next. Typical protocol would be 49 frames, so they would be now go into the depth. So what you actually see is you very sparsely cover the background of the eye, and 20 degrees is kind of very narrow. And what you would like to have next is a densely sampled pattern and cover more of the background of the eye. The densely sampled pattern is, of course, beneficial, so you could extract images in all directions. And what's also nice, if you have a densely sampled 3D data set, you have holographic information. And we already heard in the first very nice presentation how beneficial holographic information is and what you can extract. You can reset focus, you can do a lot of things. So you want to have a densely sampled wide field data set. Next. So we actually built a system that was deployed in the clinic. You see here ophthalmologists are trained. We did something like 100 patients. So the system is kind of stable enough to be used in the clinic. Next. And this would be a sample data set. Next. It actually consists of 1,900 OCT images, each consisting of 1,900 depth scans, each consisting of 1,080 pixels. And you see actually on the right-hand side, the OCT frames, very good penetration, good signal. And on the left-hand side, this is not a fundus photo. This is actually a collapsed three-dimensional data set. And this kind of shows the strengths. Very often you want to have perfect registration of your OCT scans. And if you actually can do the registration in the en face plane, where usually the doctor is used to, it's always perfectly registered. So you can actually extract OCT frames and just mark on this pseudo en face where you want to have the OCT scan and then extract it in post-processing. If you image a large data set, you never have a miss. So like if a patient comes back after a couple of years and there's a pathology, you can go back in time and kind of look if there was something before. There are not necessarily imaging protocols anymore. You don't have to decide star scan or circular scan. You just extract it in post-processing. And actually, the acquisition time was shorter. Next. So it was 2.5 seconds and everything is acquired. So push the button and you're happy. Next. So what you can do there is actually, if you do not only look at intensity, but also at the phase or at dynamics, you can actually extract flow. So this was done in collaboration with Rainer Lightgap Group. He will give a presentation tomorrow. And back in 2012, we showed over wide range, like ultra wide field, we can display flow. But this is just the first step. I think it's very popular now to look at dynamics and look kind of how the phase changes over time. Maybe by excitation, how we saw like in elastography or inherently. And if you have like a stable 3D data set with a dense sampling pattern, and it's stable because you are fast enough, you can extract much more than just like intensity information. Next. So we will also hear the imaging the eye and with OCT is very nice, but of course many regions in the body are not as accessible. So it's important to build endoscopes. I think we will hear much more about this by Brett Boomer this afternoon. So we built all kinds of different endoscopes which are capable to keep up with this high imaging speed. So top, there's a handheld rigid endoscope. This can actually even run live. On the bottom, that's collaboration with Hinnerk and Gerion Hüttmann from our institute. This is a forward-looking spiral scan. Next. Which is actually also capable to record 4D videos. So we see here, like on the left hand, some paper, and on the right hand, like this is a finger, a movie of a finger. And so this spiral scan, it's fast enough to do something like 6 volumes per second. However, in this case, this 4D movie data was recorded, but then processed later. On the right-hand side, we have a collaboration with Erasmus Medical Center. They do intravascular imaging, and they developed a very new type of endoscope, next, that actually uses a small micromotor that can spin several 100,000 times per minute, 5,600 times per second, and kind of side fire the laser beam. And this endoscope is then fast enough to also keep up with the FDML laser. And you can image several centimeters of coronary artery densely sampled in less than a heartbeat. So you remove almost any motion artifacts. All these systems actually were kind of post-processed. Push a button, acquire the data, and then analyze. However, there are situations where you want to do it live. And this is OCT for surgical microscopy. Next. So OCT for surgical microscopy is nothing new. On the right-hand side, we see a system. It's a spin-off from our institute. It was commercialized by Hawk Stride. So it's a surgical ophthalmic microscope using an OCT. OCT is very compatible with surgical microscopes because it looks into the depths. In surgery, you often want to look what's below the surface. However, classical systems, if they do something like 10 frames per second, you cannot do 3D volumes as OCT could, like you see here on the left-hand side. You are back at standard 2D slices. Because if you think about the numbers, next, If you want to acquire 320 times 320 pixel volume at 25 hertz, you need to process more than 1 gigavoxel per second. And our systems are fast enough, I hope to convince you. However, the big challenge there was and still is to do the live processing. Next. Next. So this is possible today using fast graphics boards. So this is our computer, earlier version. So we have a fast analog to digital converter, next, which streams data at 4 gigasample per second, next, to a first graphics board where unpacking, resampling of the data, apodizing, 3 million Fourier transforms per second, and dynamic range compression are done, next. And then the data is streamed at 4 gigabyte per second to a second GPU. And this GPU is doing what a GPU is supposed to do. It renders the graphics and does 3D representation. So this is possible today. Next. And then you end up with a video like this. We see here this finger acquired with, I think, 20 volumes per second. And this is running live. So you can pull this around, turn this around just as you want. And one thing that's also important, it's not only the speed that's important, that you can process the volumes, it's very important to have low latency. So if you have 25 volumes per second, but you have a lag of 3 volumes, this makes you crazy if you want to do a procedure just based on this image. Just as a side note, the system is running at 16 teraflops, so 16 billion floating point operations per second. And next. In the year 2000, the fastest supercomputer in the world had 7 teraflops. So for me, year 2000 is not so long ago. There, it's difficult because you would need to reposition the microscope over and over again. So you have, of course, like binocular, stereoscopic view, but dynamic moving is difficult. So our collaborating pediatric surgeon, next, says sometimes he does not use the surgical microscope, but that just magnifying goggles, because it's much nicer to interactively change the viewpoint. And it's actually not only humans who do this. Next. So dynamically moving to generate a parallaxis is what here these owls do. Actually, owls cannot move their eyes. So this is something that kind of lets you appreciate depth much better to interact. Next. So we wanted to choose the display, not only like a 3D display, but actually have virtual reality gear. So these are these tracked goggles where you have 2 lighthouses and they measure the position of your head, and the display is adjusted according to the angles and position of your head. Next. So we used actually a commercial system from Optores, former spin-off company. There will be a talk tomorrow, and interfaced it with virtual reality gear. Next. And tried, if it's possible, to do a surgical procedure solely based on this 3D OCT view. So Yoko Miura, she's a MD, PhD, works half at the eye clinic and half at our institute, tried to do some mock-up surgical procedure on enucleated pig eye. And she doesn't have even the camera view from the 2 binocular cameras in the VR gear. So you see actually she has some like black paper in front of it. She only sees the live OCT. Next. So in this video, we will see on the left top this camera view, but it was not displayed to her. And on the right-hand side, just a video what she does. On the bottom left, next, you see actually what she sees in her 2 eyes. And it's moving just as she moves your head. And then on the lower right-hand side, we just extracted at 1 position OCT frame. We could also create our fast presentations and whatever we want. And you see she pokes actually the eye with this needle. And what's kind of also interesting, when she withdraws the needle, you see kind of like a dynamic contrast. You see speckles flowing, like head-mounted with this virtual reality gear. Good, next. So to wrap up, FDML lasers were the first ones who enabled high quality megahertz OCT, and probably we'll see other lasers that will do the same in the future, which will of course help spread the technology. Then I showed you that live processing of this data at 3 million lines per second is possible, more than 4 billion voxels per second, and it's possible to display it with very low latency. What you saw was always less than volume latency or lag. There are several medical applications that can benefit from megahertz OCT. I showed you ultra-wide field ophthalmic OCT imaging. Then if you do some phase-based OCT analysis, especially if you do it in vivo, where you always have motion artifacts, and you do this type of numerical optics, refocusing and correcting for aberrations, this will be very beneficial. Then endoscopic OCT, and I think here it's probably almost mandatory if you do this 4D augmented reality OCT. I think there are many more applications where you really want to have megahertz OCT. So in many implementations, many applications, megahertz OCT will be there in the future. Okay, next. So I want to thank my group, thank all collaborators, thank the funding agency, and thank you for your attention.
Okay, thank you, Robert, very much for a nice talk, and always beautiful to see. It's great to see your beautiful progress. And so there are a couple of questions. One is actually about the name. Where does the name Fourier domain mode locking come from? It's kind of funny because I remember exactly the moment that you came out.
Exactly. So we discussed about this, and the problem is frequency mode locking was already occupied. So FM mode locking is a pulsed laser that has a modulator to achieve regular pulses. So you would call it frequency domain mode locking, but this is different. It doesn't sweep, it just generates pulses. So this would be like a more correct term, because that it's very complementary to standard mode locking. A standard mode locked laser works in a system. You have kind of like amplitude modulation or amplitude in phase, like just a shutter that opens and closes, a pulse goes through, you cut leading edge and trailing edge, and synchronously to the round trip of the pulse, you do this over again, and the pulse gets shorter. This can also be a passive mechanism, like the Carolens in Carolens mode locking in titanium sapphire. So you have amplitude modulation, then you get short pulses. We modulate or filter the spectrum, and we get extremely long pulses. Instantaneous spectrum of a standard mode locked is wide. Here it's narrow. But by now we proved this actually both have like a wide comb-like spectrum. So it's complementary. Should be time mode locking and frequency mode locking, but the name was occupied, and because like in our heads and Maci's head there was like Fourier domain OCT, so we called it Fourier domain mode locking. But actually the name is wrong. There is no Fourier domain. There's a time domain and a frequency domain and no Fourier domain. But the best names are always a little bit wrong, so it's kind of, you can discuss about it.
Okay, another question is, can you comment on how fast you can go with short exposure times and still have good SNR while keeping safety standards for ophthalmic applications?
In ophthalmic, it's I think now they revised the standards. All images that you will see from our group are made for a situation where the scanner can stand still for 10 hours and everything is safe. So it's 1.9 or in Europe 1.4 milliwatt, and you get something like 90 dB sensitivity, which is a little bit borderline. So this 90 dB is then at like 1.77 megahertz, 88 at 3 megahertz. If you average, it's kind of okay. However, there are commercial systems now. I think Zeiss got an FDA approval for 7 milliwatt. So you can account for the scanning. So the faster you scan, the more distributed is your image. And they only apply very slow scanning, like 100 kilohertz, and go to 7 milliwatt. And then, of course, the thing looks different. I would say for commercial systems, to get similar image quality that you are used to, something like 3 to 6 megahertz is positive. Is possible. Outside the eye, we can apply maybe like 30 milliwatt, so there's no limit. We start at the 3 megahertz system already with 108 dB. So
there is one more question. Robert, is there any chance of miniaturizing FDMLs by not using fibers, but more like some kind of micro resonators or other structures like this?
Theoretically, yes. We have thought about 3 to 4 billion of these different ideas, but all have some kind of a problem. So anyway, any resonator has an inherent structure, frequency structure in it, because a resonator generates like copies and like it's repetitive, like the structure of a laser. So theoretically, it's possible. Maybe at some point it is, but we have thought a lot about it, and it seems difficult. However, the fiber, like 500 meters of fiber, and like the volume of the fiber itself is something like 100 milliliters. So it's much smaller than the electronics and the boards, and you don't want to pack it too tight. So there are other components, and maybe the environment and temperature stabilization and power supplies and so on, that might actually be larger. So the fiber itself might not necessarily be, so just the fiber by itself, but maybe kind of like the environment and holder and kind of isolating from vibration and temperature, that might be.
Okay, so Robert, we have to move on. So thank you very much for your talk and for being with us. And now we'll move to the last talk of in this session. We will have Egidius Auxorius, who received his PhD degree in physics from Imperial College of London, and worked for a lifetime, fluorescence lifetime imaging. And now he also worked in Harvard Medical School and Institut Langevin in Paris. And now he has his own group, the Center for Physical Sciences and Technology in Vilnius, Lithuania, and also he's senior researcher at the Polish Academy of Sciences. So he will talk about full-field OCT imaging, Fourier domain full-field OCT imaging in human eye.
Hello, my name is Egidius Auxorius, and I'll talk about a very fast volumetric imaging technique that we use to image eye. So specifically, I'll talk about Fourier domain full-field optical coherence tomography and how reduction of the spatial coherence of the laser enables us to image cornea with this technology for the first time, as well as to reduce crosstalk when imaging retina. So Fourier domain full-field OCT has been around for a while, and it's based on this SWEP source and a very fast camera. It enables very fast imaging rates. However, the disadvantage of this technology is the absence of a confocal gating, which makes this technology more sensitive to multiply scattered light that in scanning OCT, for example, is rejected by a pinhole. This results in coherence noise, which is manifested as some sort of crosstalk or speckle formation, especially at deeper layers. So for example, in a full-field OCT image shown here on the right, we have this haze which appears below RPE layer, which is not supposed to be here, as confirmed by scanning OCT image. So when imaging cornea, on the other hand, we face a different problem. So we have this laser collimated beam sent on the cornea and this high resolution Linic interferometer. However, the laser gets focused on the retina to a tiny spot, and since the laser is more than 1 milliwatt, it causes a safety issue, so it can damage a retina. So we solve the two problems by using this very fast deformable membrane, which effectively destroys the spatial coherence of the laser by projecting many random phase patterns. So it can generate around a megahertz, on a megahertz scale, different phase patterns. And it's composed of two areas, this active one in the middle and the flat one. So if we were to put the membrane in this holographic imaging setup, we can see it forms fringes when the membrane is off. When the membrane is on, the fringes gets distorted and it forms a complete fringe washout in some areas because of this axial motion by the membrane. So here's an OCT system, and for those experiments, we moved membrane outside of the interferometer, and we can see in the active part of the membrane, the OCT images gets washed out with the defocus, whereas in the non-active part, where the membrane is simply a flat mirror, we see signal preservation. And this forms a basis of a confocal or spatial coherence gating, which enables us to reject crosstalk, because here assumption is that crosstalk is mainly caused by the photons coming from different layers, and this kind of axial sectioning enables us to reject those photons. So here's a simple retinal imaging system in spatially coherent case. So when the laser, the spatial coherence of the laser is not destroyed. So again, we have a swept source. The eye is put here, and there's a reference arm, and both retina and reference mirror is imaged on the camera. Now, when we try to destroy the spatial coherence of the laser by using the membrane, we use additional lenses to re-image membrane on the retina and the reference and the CMOS camera. These three lenses sit on the same translation stage, which helps us to keep all the layers aligned axially when we try to focus retina on the camera. So, and we have to do it for each individual eye because of different refractive errors present in different eyes. So when we switch the membrane on, the beam path changes accordingly. And by moving now, by adjusting this translation stage, we are able to properly image all the layers on the camera. So these are images acquired with spatially incoherent illumination in full field OCT. So this is B scan, and it shows that we can resolve choroidal structure better compared to a spatially coherent case, which we acquire by switching the membrane off. So spatial incoherent case compares well to the scanning OCT image shown here on the right. And the acquisition time and power was similar in both cases. And this particular image was derived from this wide field scanning OCT image. And all the images were acquired from this particular spot seen in fluorescence angiography image. So these are ENFAS images acquired with Fourier domain full field OCT. And again, in spatially incoherent case, we see improvement in choroidal structure. So it rejects the crosstalk, and we can see the structure of choroid better compared with the case where we don't destroy spatial coherence of the laser. The contrast of other layers also improved when we switched the membrane on, so as can be seen here. And these are various fly-through images, ENFAS and V-scans. And this is just a 3D rendering of the final data volume, which we derived by averaging 24 such volumes. So the total acquisition time of the data were less than a quarter of a second. So before averaging, before registering those individual volumes, each volume was motion and dispersion corrected, because we have access to this phase information that helps us to do dispersion and motion correction. Not only that, we can do with the phase information, but as will be shown more by David Boritsky tomorrow in his talk, we can also correct for optical aberrations and improve the image resolution and contrast further. And this is despite the fact that we effectively scramble the phase before the interferometer. So coming back to cornea imaging, and like I showed in beginning, imaging cornea poses a laser safety risk, and therefore we again introduced the membrane to reduce the spatial coherence of the laser. So we put the membrane in such a place that we can also use two lenses to re-image it on a cornea here. So when the membrane is off, again, it's a spatially coherent case, and after the lens we have a tiny focal spot here, as well as a tiny spot in a pupil plane. And when we activate the membrane, we get more or less spatially incoherent case. It broadens the spots here as well as in the pupil plane and also on the retina. And this way it lifts the laser safety issue. And here's a time-resolved speckle pattern that we get from the membrane. So if the integration time is in nanoseconds, we resolve each speckle individually. And when we integrate for 100 times longer, which is 15 microseconds, we see the homogeneous blob. So just to add a note, this is not completely incoherent case because the spot in a pupil plane is a little bit broader, it's around 1 millimeter or less, but not fully incoherent, which would be the case when we fully fill the pupil plane of this high-resolution system, the objective in high-resolution system. This just demonstrates how the safety issue is lifted. So I had an eye model simply built from a lens and a camera. When the laser is coherent, it focuses to a tiny spot of, let's say, 20 micrometers or so. When the membrane is activated, it is broadened by a factor of thousands or so in terms of area. These are B scans and fast scans of a cornea. So we see various layers of cornea, and these are epithelial and fast images showing different epithelial layers. This is nerve fiber, and then cornea, and then stromal layers. We can also see stromal nerves here, which we can probably see better in these fly-through movies. So one thing to add is that we actually not seeing the full thickness of cornea in this particular experiment, and now we can do that in different experiments. Here we see fly-through movies and fast movies going through epithelial, nerve, and now stroma layers, and we can also see some stromal nerves appearing somewhere around here. So this is just a 3D rendering of the data volumes. Again, these were different volumes averaged into increased signal-to-noise ratio, and each volume was dispersion, motion, and aberration corrected. So as I said before, not full thickness was acquired of the cornea. To do that, we ran a separate experiment where we captured endothelial cells that were missing from the previous experiments. So zoomed in version of that image compares well to a gold standard of endothelial cells imaging, which is specular microscopy. And this image was acquired in just below 20 milliseconds. So we wanted to increase the signal-to-noise ratio by averaging more volumes. However, the hexagonality of cells are somewhat not improved, and the signal-to-noise ratio is, but not the shape. And that could be explained by the fact that hexagonality is only preserved in one particular plane, as shown in this fluorescence study. Below that plane, it acquires a different shape. And here, since we were averaging, let's say, 15 different volumes, our probably registration algorithm was not good enough to accurately align those volumes axially, and if we don't do that successfully, this blur occurs. So there's a further need for, in this particular case, defocus. So we're trying to arrive at the best image, which would be least defocused. And we also perform segmentation at the same time. So we kind of can choose the segmentation image which we like the most. To be honest, in this particular case, all the results similar look equivalent. However, it's just to demonstrate the capability of this technology, which is use of phase information to improve images. So if we go back to this corneal system, we note that the area here, which is conjugated to pupil plane, is not filled. It's not filled completely. And it allows us to insert a mirror as a hole. So the mirror does not reduce the power which is going on the cornea, nor does it reduce the signal detected by the camera. However, since half of the signal from the cornea goes back to the source where it's lost, we can use this mirror to collect some of that signal, because signal from cornea will be scattered across many different angles. So if we do that same thing for reference beam as well, by simply tilting slightly reference mirror, we can also collect a reference signal, and therefore enable, OCT imaging in this port. So here we put a line camera, which allowed us, to implement a fast preview mode. So a problem with these very fast cameras is that it has a relatively low speed of data transmission between the camera and computer, which gives us a slow preview mode. We only can get a couple of hertz preview mode with limited field of view. And a regular camera, which costs around $1,000 or $2,000, can enable us to have a relatively fast preview mode of 100 hertz, which is more than enough for our purposes, which becomes very important, for example, when imaging cornea or retina in vivo. So with that, I'd like to conclude by saying that we were able to demonstrate cornea imaging with this volumetric imaging technology for the first time by simply reducing the coherence of the laser. It also reduced crosstalk in retina images. Probably we reduced crosstalk in corneal images as well, but we did not have a way to check that. And on the other hand, crosstalk shouldn't be a significant problem in cornea because of its relative transparency. And crosstalk mainly occurs in scattering tissues such as retina. So we also used phase information to correct for motion and chromatic dispersion, as well as optical aberration, despite the phase scramblings that we perform with this fast deformable membrane. And this technology compares well with other technologies available now for full field OCT imaging. It's much faster, also being also a little bit more, quite significantly more expensive, but the price we expect will go down with this price reduction of the camera. And with that, I'd like to acknowledge help from i-POB Group, the funding sources, and thank you for your attention.
Okay, thank you very much. It's good to see you, Egidius. Hi.
Hello.
So I have a couple of questions for you. So one is, does turning DM on in cornea imaging also effectively makes illumination numerical aperture higher? What are the implications for OCT?
It does make a little bit higher, not significantly, because like I showed, we only expand the pupil plane by, to up to 0.5 millimeter or so, which is a relatively low NA. But that is enough for us to see the effect which we are seeking, which is basically crosstalk reduction. So that's the main implication. So it does limit depth of field, but it's still within the range so that the Fourier domain OCT would work, which is important, right, in a Fourier domain to have a significant depth of field so that you can have a relatively large imaging depth. So yeah, and as I mentioned before, we're not filling the full pupil plane, which would narrow our axial range. So although it would increase the performance further by further rejecting crosstalk. But I think we are somewhere in a sweet spot right now with this illumination.
So another question is, will it be possible to sidestep the requirements for a fast camera by encoding full field interferograms in space? Meaning that you can use a very large array of megapixels and then get simultaneously all these different spectrally encoded images.
Yeah, probably. The problem will be, I guess, in the rest of the optics, how you implement that. Yeah, assuming that we have such cameras, which I think we do, and they are much cheaper. But I see the problem in generating those multispectral interferograms simultaneously. Yeah, it's a good question, but complicated thing to do.
Implement. And so maybe one more question. How do you think from your experience, because we have this industrialization potential here, is this system stable enough to be useful in the clinic or environment outside the laboratory?
Yeah, by definition, I think it's possible to do that because it's one of the fastest techniques, so it's a good technique to use in vivo environment, right? So because we need to acquire data as fast as possible, so I think it's perfect for in vivo applications, and we do see that we can use it for even for patients. So it's yeah, it's possible.
Okay, great. Thank you very much, Egidius, for being with us.
Thank you.
So see you around. And we have, before we start short break, we have just a short announcement about the SPIE chapter that we created recently. So Monika is our SPIE chapter chair, and she can tell us a little bit more about that.
Thank you. So hi, everyone. So today is a very good day for SPIE chapter openings because of the conference which is related to optics as well. So we are going to announce an opening day for SPIE student chapter, so which was approved in September 2020 in our institute. So we are very glad to announce that this will be a beginning for many more adventures in science to discuss and share the knowledge as a common platform among IPC students. So we have Professor Maciek Witkowski as our chair and advisor of the SPIE student chapter. So he would be guiding us through this. And we have the members. Myself, I am a president of SPIE, and we have Ahmed, who is a vice president, and Myunj, who is a secretary, and we have Nalin, who is a treasurer. And we have many benefits from the SPIE student chapter, so especially for the IPC PSS students who are not well aware of the student chapter, since it's established very new. So we have student services, scholarships, grants, and career development programs from SPIE. So we have student leader workshops. So every year we have two main major conferences in optics, which is SPIE Photonics and SPIE Optics plus Photonics, which is in Washington, DC and San Francisco. You have a travel grant where you can be able to attend SPIE leadership program. And this will enhance your communication skills, and you can be able to portray yourself and learn a lot about how to manage the student chapter, and also to have an interaction with the professionals. And you also have a lot of scholarships and outreach programs in this. So these are the couple of scholarship programs where you can be able to apply for the grants. And you have a student author travel grant. So in order to present a paper in a conference, you can apply the funding to SPIE. To attend the conferences. And you also have a SPIE career development programs. So you can also attend the job fairs as well as SPIE career summit and the career labs. So we have our plan for the future, where we plan to organize many workshops, optics puzzles and games and talks in order to support our student chapter. Thank you for giving the opportunity.
Okay, thank you very much, Monika. So now we can conclude this session, and I would like to invite all of you for a short break. In 15 minutes, we will start our keynote session. So please take rest for a while, and we will be back here soon. Thank you.
Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin. Zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Światło to jest niesamowite zjawisko. To jest podstawowy składnik materii całego wszechświata, który tak naprawdę spaja wszystkie atomy, molekuły, wszystko co znamy. Światło definiuje czas i przestrzeń. Jest zupełnie niesamowitym czynnikiem, który my jako ludzie możemy odbierać bezpośrednio za pomocą naszego wzroku. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. W tym właśnie zajmuję się ja i mój zespół.
Użyć urządzenia, które poniekąd są magiczne, bo pomagają diagnozować choroby różnego rodzaju, które normalnie nie są widoczne gołym okiem.
Nauka obok sztuki jest jednym z najważniejszych aspektów działalności człowieka. Sztuka może leczyć duszę, ale nauka może leczyć ciało. My zaczynamy od oka.
Fajnie współpracować z ludźmi, dla których rzeczy niemożliwe nie istnieją. Myślę, że najlepsze słowa opisujące pracę u nas w zespole to mierz wysoko i sięgaj celu.
My research aims to better understand how human eyes work. To me, being a scientist is having the opportunity and the beauty at the same time of learning something new every day.
W naszych projektach cały czas staramy się, jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki pod skórą, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Jesteśmy blisko tego, widzimy już światełko w tunelu, jesteśmy coraz bliżej, ale to jest początek drogi.
The cornea is the most external lens in the eye. Along with the crystalline lens, it projects the images of the outside world onto the retina. The cornea is a transparent dome, and its structural integrity relies on finely interleaved collagen fibers. The regular shape of the cornea is, therefore, the result of its biomechanical rigidity. However, the cornea is not a piece of plastic, and different corneas may respond differently to mechanical stimuli. In several pathologies, such as keratoconus, the cornea weakens locally, resulting in corneal bulging and vision distortion. Keratoconus affects 1% of the population, and treatment requires implanting a supporting structure inside the cornea, intracorneal ring segments, or stiffening the cornea, instilling a dye and irradiating with light, a technique called cross-linking. There are other ocular conditions in which the cornea is reshaped or surgically open. These conditions are highly prevalent, such as myopia, that affects 30% of the population in Western countries and 90% in some Asian populations. Presbyopia, the age-related loss of dynamic focusing capacity, which affects 100% of people older than 45. And cataract, the loss of transparency, which affects 50% of the population older than 65. In corneal refractive surgery, used to correct eyes' refractive errors, a laser is used to sculpt the cornea into a different shape. Alternatively, new techniques are being developed where biomaterials or tissue is implanted in the cornea to correct presbyopia. In cataract surgery, an intraocular lens is implanted through an incision that needs to be made in the cornea. While all these treatments rely to a larger or lesser extent on the mechanical response of the cornea, today there is no clinical instrument that either detects corneal mechanical abnormalities or can help in predicting the mechanical response to surgery. i-POB, a project funded by the European Commission Horizon 2020 program, addresses this unmet medical need. i-POB has gathered a reputed multidisciplinary group of experts in academia, industry and clinic to deliver and demonstrate a new clinical instrument which will put Europe in the forefront of personalized diagnostics in ophthalmology. The partners of this highly international consortium are Project Coordinator, Biomedicine at the National Research Council, a pioneer group in optical imaging eye diagnostics. Academic partners, Polish Academy of Sciences and the National University of Ireland Galway, both world leaders in biomedical optics and photonics, and University of Liverpool, experts in corneal biomechanics. Two Eyes Vision, Oculus, Optimize and iRock Science, all international companies selected for their unique technical expertise in the ophthalmic industry and strategic position in the field. World most prestigious ophthalmology clinics, Moorfields Eye Hospital and Instituto Oftalmológico Fernández Vega, both with flows of thousands of patients per day. The multidisciplinarity of the consortium will ensure an efficient translation of the front-end laboratory designs and prototypes into a viable instrument that will be tested in pilot clinical studies with patients. i-POB, bringing light-based technologies to improved diagnostics and personalized surgery.
Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
Good morning, everybody. We start now the session 2. First, I will present my person. My name is Christophe Gorecki. I was the director of research in France at the CNRS. Now I am retired from the CNRS and I am the member of ICTER. So this session will include 2 speakers. The first one is Brett Bouma from Harvard Medical School in USA. Mr. Bouma is professor of dermatology at Harvard Medical School, and his talk is entitled The Development and Commercialization of Endoscopic OCT Technology. Please, Brett.
Well, hello, afternoon. Thank you for giving me the opportunity to participate. As one of the earlier speakers, Brendan, mentioned this morning, it's a disappointment that we aren't able to be there in person, but nonetheless, thank you, Machi, for organizing such an excellent conference. Yeah, so my focus was going to be on what is effectively sort of a case study of the commercialization of endoscopic OCT technology. Next slide, please. Next slide, please. So as we've gone through this morning, OCT was developed in the early 90s, primarily to address issues in ranging in the eye, measurements of the eye, and then for imaging both the anterior, the cornea, the lens, as well as the retina in the eye. Next slide, please. My focus was on, when I joined the group at MIT in '93, was on answering the question whether OCT could be directed towards other applications in medicine. And a focus early on was on the field of oncology and cancer, and recognizing that cancer was the second leading cause of death in the United States, with multiple needs for improved imaging, and focused on the realization that GI cancers, gastrointestinal cancers, offer a particularly unique access and opportunity for improved outcomes through early diagnosis. Next slide, please. Is there any way that the inset picture could be moved on the screen? I can't see the slides. Next slide. Back one slide. I can't. No? The inset picture in my display is covering a portion of the slide. If you could go back one slide, please. Okay. So one particular cancer was the focus of our early technical work, and that was esophageal adenocarcinoma. It was associated with a rising incidence in the United States and, in fact, the world. It's associated with a low survival, a high morbidity, and it's recognized that early diagnosis is critical because it allows improved intervention. Key to this, the application of OCT for this disease, is that there's a very well-defined at-risk population that is recognized through the presence of refractory reflux disease, so chronic heartburn that doesn't respond to drug therapy. Next slide, please. The understanding of the progression of the disease is from this metaplasia, specialized intestinal metaplasia that arises from chronic reflux of gastric acid from the stomach into the esophagus, which by itself is benign, but it reflects higher probability of progression through low-grade dysplasia onto high-grade dysplasia and to adenocarcinoma. The changes that I'm describing here are epithelial, lining the esophagus, so they're readily accessible by endoscopy. Next slide, please. The challenges for endoscopy is that it's not visually apparent in all cases the difference between metaplasia and the distal portion of the esophagus. So identifying regions by white light endoscopy alone is not straightforward. Next slide, please. This disease presents 2 separate challenges for the endoscopist. The first is in screening this very, very large patient population of 30 to 50 million in the United States who have chronic reflux. And for that large of a population, endoscopy is too expensive. and that's primarily because it's associated with conscious sedation and what amounts to a full-day procedure in an endoscopy center. Additionally, the sampling of endoscopic procedures is low. At best, we can take a few biopsies and sample something like 1% of the potentially involved epithelium. So screening for a microscopic disease is not a very good approach to take these small biopsy samples. Next slide, please. In addition to screening, there's a requirement for improved technology in the realm of surveillance. Once a patient has known metaplasia or Barrett's esophagus, the protocol is to put them on a regular endoscopy surveillance protocol where they have endoscopy plus 4-quadrant biopsies at a period of something like 2 years or 2 or 3 years. In this procedure, although maybe a dozen biopsies could be acquired, it still reflects only a sampling of something like 1% potentially involved epithelium. And it's recognized that there are many cases of undiagnosed cancer common in high-grade dysplasia that go undetected in endoscopy. And in addition, there are cases where the finding of high-grade dysplasia is thought to be sufficient to trigger esophagectomy. Esophagectomy is done, and it's found that there is no actual presence of cancer. So there's a need for improved surveillance of these patients with known metaplastic change. Next slide, please. So again, two separate diagnostic challenges in screening, very large patient population, surveillance in a smaller patient population but at elevated risk. And this was the launching point of the early work in, say, 1993, asking the question, can OCT be converted from a technology that was really specialized for ophthalmic imaging into this realm of endoscopy? Next slide, please. And this would require several advances. First, answering the question, could OCT be could it perform well in highly scattering tissues? The eye is very unique because it's highly transparent. And low scattering, the tissues of the rest of the body, and particularly the esophageal tract, are highly scattering. Could suitable catheters be developed for insertion through the instrument channel of endoscopes? And could OCT be maybe modified or improved to overcome the motion artifacts that were known to be present in the esophagus through peristalsis, the proximity to the heart, so the heart is beating as well as breathing? Next slide, please. The first system that was developed to test some of these improvements was based on a mode-locked femtosecond laser with continuum generation at 1300 nanometers. The longer wavelength was chosen to allow better penetration, lower scattering in the esophageal wall. We developed a rotary junction to connect to a spinning catheter and the catheter itself, using a very small gradient index lens and a prism to deflect the beam transversely to the catheter. And we also addressed the question of image acquisition speed by developing a faster way to do the coherence delay in the coherence domain ranging system. And that resulted in a few kilohertz of A-line rate acquisition, which was sufficient to avoid most motion artifacts. And the first animal studies were conducted in 1996 by bringing a rabbit into a laboratory which comprised several optical tables, meter by 2 meter long tables, connected together by fiber optics to make this system. But basically it was a proof of principle demonstration that OCT could actually work, as these images show, to acquire cross-sectional images of tissues of the esophageal tract. Next slide, please. So in about 1997, late 97, I started a laboratory at Massachusetts General Hospital, and the first focus was on developing a clinically viable version of the system that we had developed at MIT. In the picture on the right there, you see the early prototype. But the idea was to develop a portable system that could be brought into the clinics to test the feasibility of making these types of images in living human subjects. Next slide, please. The first pilot study was really focused on feasibility, and the endoscope was inserted into a patient. Our catheter was inserted through the instrument channel and held in proximity to the esophageal wall and the stomach, and we collected images of normal esophagus, normal stomach, and just tried to assess whether or not we could see deeply enough within the epithelium to characterize disease progression associated with esophageal adenocarcinoma. The results were actually very surprising because we had previously imaged cadaver esophagus and stomach and found a completely different result. We later learned that that result was misleading because of post-mortem reflux and degradation of the tissue. In the living human subjects, we actually saw a vibrant layered structure in the esophagus and the crypt and pit architecture that's characteristic of the stomach. Next slide, please. That feasibility led us to conduct a little bit more in-depth study of patients with disease. And the question there was, could OCT images provide contrast between these normal tissues of the upper GI tract as well as metaplasia and then dysplasia and adenocarcinoma. And in the early studies, we found that there was a pronounced change in the normal layered structure of the esophagus, which signaled the onset of the disease progression. And we tried to identify specific characteristics associated with the different stages of progression. Next slide, please. So these early clinical studies confirmed the feasibility of endoscopic imaging and disease identification, but they also pointed out some of the deficiencies of the technology that really needed to be rectified before it could make an impact. And first and foremost was the fact that what we were doing was effectively an optical biopsy. We were holding the probe at a discrete location and collecting a cross-sectional image of the tissue, akin to taking a biopsy and sending it to a pathologist. And that doesn't overcome the need for this comprehensive interrogation of the distal esophagus. We would still at best sample some 1% of the surface area of the esophagus, and the need was to do screening. The problem was that OCT was already performing at the sensitivity limits in terms of speed, and speed was the limiting factor. We couldn't image faster, we couldn't collect images over a larger range. So these observations required technical innovation, and for us, the focus was on collecting images more rapidly. Next slide, please. So in 2003, roughly, we began to investigate frequency domain collection of the ranging data that was the basis of OCT. It was well known that by changing from the coherence domain scheme of having a broadband light source and mechanically scanning the delay of the reference arm to a system that had a narrow wavelength, very highly coherent light source whose wavelength swept over time and keeping the reference arm fixed, it was known that that was a sufficient paradigm for collecting ranging data. What wasn't known was that there was a significant benefit to that approach in terms of sensitivity. And that was the real breakthrough. There were three papers that came out in 2003 that showed theoretically that this scheme and the analogous scheme of spectral domain OCT provided a sensitivity advantage which could be on the order of something like the number of pixels per A line or something on the order of 1,000. So it collects the same information that was collected in time domain OCT, but it did so on a much more sensitive basis, and therefore it could support a higher speed. The problem was that there weren't any lasers available. You couldn't go to the internet and buy a laser that swept monochromatic light source rapidly. So it required innovation in the laser space. Next slide, please. Next slide, please. So in addition to advances in laser design, realizing a faster system for esophageal or endoscopic imaging required improved methods for data acquisition and processing, a rotary junction that could spin at a very high rate, better focusing optics in the distal catheter, and a way to regularize the core of that spinning catheter within the esophagus, which is undergoing peristalsis and normally would collapse upon the probe. So we developed a balloon probe which held the optics on the center. It scanned like a lighthouse. Each revolution gave a cross-sectional image, and that core could be pulled back within the balloon to map out the cylindrical volume of the esophagus. Next slide, please. Each of these technical innovations led to, and if you could go ahead and start that video. Maybe advance the slide, there you go. So this was one of the very first images that we collected with frequency domain, or OFDI, also known as swept source OCT, in a human esophagus, showing the full layered structure of the esophageal wall. In the epithelial layers, you see structures that are vessels running longitudinally within the esophagus, and we can actually see there all the way into the muscularis propria, the muscular layer of the esophagus that's responsible for the constrictions of peristalsis. And again, this was acquired through a balloon. Next slide, please. By collecting that cylindrical volume, we have now the volumetric data that can be displayed in many different interesting formats. The panel on the left there, A, is as if the esophagus was sliced and opened longitudinally with the mouth at the or the proximal end of the esophagus at the upper portion and the stomach at the lower portion. And you're seeing there an image which displays some of the vessels within the wall of the esophagus. And then at any arbitrary location within that field, you could produce through the digital, through the three-dimensional data set, a cross-sectional view corresponding to that location. Next slide, please. So at each step along that process that I've described so far, going from the first demonstration of a catheter-based system in an animal to a portable system that functioned sufficiently for mapping out the entire esophagus in a human, there were many innovations that represented intellectual property, and as a result, we developed a very large portfolio of patents associated with those innovations. And those patents were relevant to multiple different clinical applications, for example, in cardiology for cardiovascular disease, as well as in this field of endoscopy, maybe in pulmonary medicine as well. So the strategy that we developed to disseminate this methodology was through licensing as field specific. So we found a partner in the cardiovascular space to develop a coronary catheter for imaging, and we licensed some of the patents back into the field of ophthalmology with Heidelberg Engineering, and we also went on we evaluated different strategies for developing the technology for endoscopy. Next slide, please. And the approach that we chose to pursue was through a venture capital funded startup named 9 Point Medical. This was launched by two venture capital funds, one located in Boston and one in San Francisco. And they brought in not only a large amount of money, but also quite a bit of expertise and connections. They identified a specific CEO who was the former chief medical officer for Boston Scientific. He was a medical doctor. He had led successful startup companies in the medical device space. And with his connections at Boston Scientific, they also brought in several engineers who had many years of experience in developing medical devices. So the venture capital funding not only accelerated startup with infusion of a large amount of money, but also with this expertise in building a company in the medical device space. Next slide, please. So the strategy that was developed was to quickly replicate a device that functioned just as our device did at the academic center. That image on the right is actually one of our academic systems, but the first prototype from 9 Point looked very much like it. It was covered up better. It had better skins, as we called them, or appearance. But the point of this first product was not to be sold widely. It was instead to put it into the hands of leading endoscopy centers to get critical feedback on the important design parameters for a commercial system. It was also intended to get FDA approval and to start to work. Next slide, please. The information that was gained from that was put into the design of the first product, which was labeled at the time Gen 2 or Generation 2 product. And this was targeted to be sold to leading endoscopy centers on the size, the numbers of maybe several tens or up to 100 type units throughout the United States. But really the point was still to be on the receptive end of information and to listen to the customers and to provide that information back to the engineering team to iterate the design. Next slide, please. I can't see that portion of the slide, so I don't know what I was saying here. Next slide, please. Okay, so the idea was by inserting the balloon through the instrument channel of the endoscope, we could map out the full volume of the esophagus. We could potentially identify through the OCT images regions that were suspect of being, for example, high-grade dysplasia. And the next step, of course, would be to tell the endoscopist, this is where the disease is, this is where you should go back and biopsy. So the question quickly became, how do you convey this information back to the endoscopist in a way that will allow them to navigate to those very small spatial structures within the esophagus that they can't see through white light endoscopy? Next slide, please. So sorry, didn't realize. Okay, now I can see better. So we came up with the paradigm of markings. By the image on the upper left there was an image of the balloon inflated inside the esophagus of a patient. From that, we collect, again, this volume of the cylindrical volume of the microscopic data. We can use that to identify suspect regions. And now, without removing the balloon while leaving it in place, we introduce a laser that has sufficient power to coagulate very superficially the lumen of the esophagus to leave a laser tattoo, if you will. By deflating the balloon, you can pull that back out. Now the endoscopist can go back and identify the regions to be biopsied based on the locations of those marks. Next slide, please. The question was what type of laser would be sufficient for that. That required additional innovation. We focused on a Raman frequency shifted deuterium dope fiber as a design, and that gave us very sufficient power to give these very rapid coagulation marks. Next slide, please. Prototyping that in ex vivo tissue showed that on the left you could see the lesions we were inducing in the OCT image, and on the right, it's a little bit hard to see in this display, but you can see the small little white coagulation marks, and that image was acquired by an endoscope. Next slide, please. And then we also had to make this process compatible. Go ahead and advance that slide. Process compatible with the balloon implementation, so make sure that we're not going to destroy the balloon or pop the balloon, if you will. So that actually worked out pretty well. Next slide, please. So another key finding from the dissemination of something like 50 of these systems throughout the United States was, as we stepped from working with the key opinion leaders or the clinical champions, which was, let's say, a smaller cohort of 6 to 12 endoscopists who had worked with many different prototype endoscopy instruments over the years, they adapted to our image findings and the interpretation of the images very rapidly. What we found was when we disseminated these systems to a very much larger cohort, training the community, training the endoscopists to read the OCT images was much more challenging. So it became imperative that we focus on better ways to guide the user's interpretation of the image. And we used the fact that we had many systems out to generate large data sets. And of course, that supports the use of artificial intelligence or machine learning. And when we embarked on that process of developing machine learning algorithms for image interpretation, we immediately recognized that this would be a challenging approval process for the FDA. So we approached the FDA, told them what our plans were. They gave us guidance and feedback. And our work jointly led to the first FDA-cleared artificial intelligence product for gastroenterology. And the point of this product, though, was to, again, provide diagnostic information, image interpretation information to the endoscopist, as opposed to requiring all new endoscopists to learn how to interpret the images. Next slide, please. So what I've been talking about to date, so far in the presentation, is a technology which addressed the need for surveillance. So once patients are known to have metaplasia, they are brought into the endoscopy unit. They're already there. We can put our probe through the instrument channel and improve the process by surveilling the entire esophagus as opposed to just a few biopsies. Next slide, please. What I didn't talk about was a way to solve the requirements for screening. Screening needs to be done on a very much larger patient cohort, and for the numbers of patients that have refractory reflux disease, endoscopy is too expensive. Next slide, please. So one of my colleagues, Gary Tierney, promoted the idea of using a tethered capsule. And the idea here is that this could potentially be brought to the esophagus for esophageal imaging without the need for the endoscope, and therefore without the need for conscious sedation, and therefore could potentially be done inexpensively. Next slide, please. This is one of the very first procedures that was done at Massachusetts General Hospital. A volunteer is given the capsule, and obviously they're not sedated, they're sitting up, they're awake. They swallow the capsule with the help of a drink of water, and as the capsule is brought down into the esophagus through swallowing, peristalsis begins to take it down into the stomach. Once it reaches the stomach, peristalsis action ends, and then the operator can actually manually feel the presence of the gastroesophageal sphincter by trying to bring the probe back up. Start imaging. Next slide, please. Advance the slide, please.
I'm going to start recording on you.
Okay, so now we're going to be advancing.
If you advance the slide, the images will appear. Well, okay, let's go with that. But a video should have appeared showing the images that were acquired by that capsule. But the bottom line is that this capsule was capable of acquiring very high resolution, high quality images of the entire esophageal wall without conscious sedation, without the endoscope. Next slide, please. Okay, so to summarize that commercialization effort, we started with an academic prototype which was based on innovating many different technical hurdles that led to a portfolio of patents that supported the venture capital funding of a startup company, 9 Point Medical. They worked through the process of establishing reimbursement billing as well as regulatory approval. They did that by building what they called the Pathfinder or early system, which was designed to be produced in quantities of let's say just a half a dozen to be put into the key opinion leaders endoscopy units to provide product design feedback. That information led into the design of the commercial product, and then that system was put out into a larger number of clinical centers, and that the information was continually used to feedback and refine the product. Next slide, please. So in summary, to think back that in '93, when OCT was first used for ophthalmology, we first worked on developing a system suitable for endoscopic imaging that was used in the first animal studies in 1996, studies in 1998, the advent of frequency domain imaging, which was really the point at which the technology became practical for clinical use in 2003. The first human pilot studies with the frequency domain systems at high speed were in 2006, and the company launched in 2010. I recall back to 2010 launching the company thinking that it would be maybe a couple of years before we had a successful product, and here we are at 2010. 10 years later, after a total investment of something like $100 million through 3 rounds of funding, involving both the initial venture capital as well as strategic investors, leading to something like 100 systems available in clinical centers, capable of laser marking, using artificial intelligence for image interpretation, and having a capsule in the early phases of clinical pilot studies as a commercial product. Next slide, please. Okay, so one of the lessons I think in this case study of endoscopic instrument medical device development, simple versus complex technologies. When we launched this effort in OCT, we were a group of engineers and physicists who I think underappreciated the complexity of OCT technology. We actually thought that it was a fairly simple technology. In commercializing it, one realizes that the subtleties of interferometry, either frequency domain or time domain, are complex to manufacturing, and that does push timelines out. But in general, the pathway to med device development is quite long. I think that that's shown over and over again, regardless of the technology. The process of iterative refinement of the product design is really pivotal in terms of meeting a well-defined clinical need. And I didn't have time to talk about the pros and cons of venture capital startup versus, say, grassroots startups, which would progress much more slowly, and I don't think are a good model for this type of technology. But the other approach is licensing patents to a large entity, a large company like we did in the cardiovascular space. That company was able to produce a product for intracoronary imaging and get that product out in in an analogous way to the VC funded, but there are a lot of pros and cons to both. Next slide, please. I captured work spanning many years. I'm sure that I'm not representing nearly all of the people who have been instrumental in that work, but I do want to point out that funding for the development of OCT, both within my own research as well as the bigger OCT community, has come substantially from the federal U.S. government through the National Institutes of Health, primarily in IBIB. And without that funding, I think that the early years of tech development in the United States just simply wouldn't have happened. I think that no company would have stepped in to pick up a product development at that early of a stage. Okay, with that, I will stop and take any questions.
Thank you very much for this very wide and interesting talk. So we have the time for 2-3 questions. The first one is, you're speaking about the high resolution of the capsule. How much is it?
The resolution of the capsule is similar to that of the balloon. It's something like 6 to 7 microns axially and something like 20 to 25 microns transverse. But the capsule has the advantage that the wall of the capsule is rigid acrylic and it can have excellent optical quality, whereas in the endoscope, the balloon and the inner lumen of the balloon are plastics that have poorer optical qualities. There's a little bit more aberration in the balloon probe than there is in the capsule.
The second question is, could capsule be used in place of normal, not OCT endoscopy? And if yes, why did not superset endoscopy yet?
I think that for the screening tasks in early diagnosis, the capsule will be the preferred modality. I think that that will become the product that will be widely disseminated as opposed to endoscopy. So I think it's actually a superior product or approach for screening. The challenge as far as medical device development dissemination is concerned is that it's a completely different customer. The proposal would be to sell that device to not an endoscopy center, but instead to a general practice, for example. But that would mean putting it in the hands of a unit or a clinic that doesn't have endoscopy expertise, and therefore the utilization of these artificial intelligence, machine learning algorithms for image interpretation become really pivotal. So I think that as far as the screening protocol is concerned, the capsule is really the way to go.
Okay. I have another question concerning the capsule. Could you extend the functionality of this capsule by addition of mobility and release of this captor? I suppose by superposition on the robotic arm.
Yes, I think that there are definitely many different ways where you could mechanically actuate the position of the capsule. Whether that's required for this specific challenge in screening patients with refractory reflux, I'm less convinced. I think that this peristaltic positioning of the capsule on the way down and then retraction on the way back up is a perfectly suitable approach. If you wanted to, for example, image the colon, I think the challenge is much different, and their navigation would be important, but also the tether becomes, I think, a poor model. So I think that there is definitely room for technical innovation in other specific clinical applications.
Okay. There is another question concerning the extension. Could you comment on what OCT extension, for example, elastography, polarization, angio, etc., there are feasible, reasonable for scan time in G-track scanning?
Yes, I think that each of those innovations has the potential to improve.
I have last question concerning the cost of the capsule. This seems to me a very interesting solution. I suppose that it's not so expensive. How much is it?
That's a great question because I think your question really is how much will it cost when it's produced in large commercial quantities? And there's two answers to that. One is what does it cost the manufacturer to produce? That number I think is quite low, and that could be on the order of tens of dollars. The other question is what will it sell for and what will it be reimbursed for? And that my guess is going to be on the order of several $100s.
Okay.
Those are just guesses.
Because looking on your video, it seems that the technology of capsule is relatively traditional. It's glass technology, yes. I suppose. I have last question concerning how about, what do you think about the interest of use the MEMS mirror for the scanning in OCT?
Yeah, I think that in the capsule that makes a lot of sense. There are image artifacts associated with our paradigm of rotating drive shaft. The reason that we chose that paradigm was really because it interfaced with the existing consoles for endoscopic imaging, through the balloon. Now with the capsule, I think as a product refinement, it does make sense to use either a motor or MEMS scanners within the capsule, and I think there's already been good progress on that tech development.
Okay, thank you very much for your talk again. And we pass to the second speaker of the session. It is Melissa Scala from Mordridge Institute of Research at University of Wisconsin. Melissa is passed his PhD in 2007 in bioengineering at Duke University, and she's associate professor at University of Wisconsin, but also investigator at the Mordridge Institute for Research at Vanderbilt University. Please, Melissa.
Hello, my name is Melissa Scala, and I'm here to talk about label-free optical sensing of cell state during biomanufacturing. So this is my background. This is a lake we are on in the University of Wisconsin, but unfortunately, I'm not sitting on the lake. I wish I were there with you, but this is fun anyway, so thank you for the invitation. Okay. So what I'm going to talk about today is cell manufacturing, and specifically CAR T-cell therapy, which is chimeric antigen receptor therapy. So the EU and the FDA have both approved these same two CAR T-cell therapies, Chimera and Yescarta, and these are for specifically B-cell lymphoma and leukemia. So the reason that these are really great therapies is it improves the outcomes of patients, but it's complex and difficult to make these therapies, as you'll see. And they are a new type of therapy, these cell-based therapies. So there are many clinical trials currently running on CAR T-cell therapies and many other cell-based therapies. So this is an important area of development both in Europe and in the US. So what are CAR T-cell therapies? We take T-cells and we re-engineer them, and they're specifically given an antibody on the surface of the T-cell that then recognizes, in this case, a B-cell that has become cancerous and kills it. And this is one way that we can attack cancer cells in the body. It's actually pretty complicated though. So we have to harvest T-cells from the patient. So this is called a leukapheresis step. And then we re-engineer those cells to express that antigen on the surface of the T-cell. And then we have to expand the T-cells. So we have millions and millions of these T-cells in the final product. And there's some quality control release criteria that is then used to administer it to the patient. So this is how the clinical trials have gone so far, and this is how the development of the manufacturing of these T cells has gone so far, but there's many, many areas to improve. So this is one example of areas where we can improve this process. Each line in this graph is the minimum and maximum percent of CAR T cells within a product within one clinical trial. So then the different lines refer to different clinical trials. And this is a few years old, but you can see that there's high variability in the percent of CAR T cells that are actually in the product that is given to the patient. And that varies within a study and between studies. So this is one area in which we can improve the quality control of these therapies. So this is important now because we have these 2 FDA or EU approved therapies. And so that has opened the door for many more therapies to be approved and used in patients. So now is the time to really tighten up this quality control so we can get more of these therapies into patients. And also, we could reduce the costs of producing these therapies for each patient. So actually, the UK rejected the use of these CAR T cell therapies because they are prohibitively expensive. The last I checked, they're about $375,000 per patient, per administration. So one way to address both of these issues of quality and cost is through improved manufacturing processes. So let's zoom in a little bit into what that manufacturing process looks like. So we talked about the leukapheresis step. That's just where the immune cells are extracted from the patient. Then we use antibody-coated beads, so it's a tetrameric antibody, and that is used to activate the T cells because they have to be activated to incorporate this antibody, the CAR transduction step. And then we expand those T cells in culture for a long time until we get many, many T cells. And then we have to remove the beads before we can put them back into the patient. So I should mention most of the therapies we're working with are in children. And for these children, they have, first they have chemotherapy, and then they have a bone marrow transplant. And so this is a 3rd-line therapy. So they're already very sick, and they've already gone through a lot. And this process is incredibly complex. It takes 3 weeks. That's actually pretty optimistic. And the initial immune cells taken from the patient, especially if they're very sick patients, can be very poor quality. It takes a lot of time and reagents to check the quality of the product throughout the process. And what we find in the end is that many of these T cells become exhausted. So that's actually a immunology term. It's a real term. It means that they don't produce cytokines. So that means they're not doing their job in killing cells around them that they're supposed to be. So one analogy is saying that you're asking these T cells from this cancer patient to run a marathon, and then you put them in the patient and you ask them to fight a war. So it's a long and complicated process, and often the T cells at the end are not what we want them to be. So in my lab, we think a lot about metabolism. So we were thinking about how could metabolism be a marker of how well this manufacturing process is working, and perhaps a way to refine it and improve it. So we know that T cell activation, which is that first part there where we're incorporating the CAR transduction, we need to have activated T cells for that step, and activation of T cells is actually a metabolic switch. So very important. We also know that glycolytic inhibitors improve T cell product efficacy, and that if we can enrich or separate cells with the right metabolic profile from those that have the not right metabolic profile, we can improve the quality of the product and the efficacy of the product. So all of these things point to the fact that perhaps T cell metabolism could be a useful measure in improving this process. Currently, what people are using in CAR T cell development and in quality control of clinical products is flow cytometry. You're probably familiar with this. It's very common. We just use a fluorescent label, and we conjugate that with an antibody to the cell, and then those cells that express surface antigens are going to fluoresce, and that's how we can see what color is associated with what cell, what they're expressing. So this is commonly used. It's great, but it's time consuming. It takes a lot of reagents. There's long prep time, which is especially important in this process. You have to actually take the cells out of the product and then assess them. So you can't continuously monitor the product and flag for when you need to intervene and improve the process. Within biomanufacturing, people are really pushing for closed loop systems. So that means they want to be able to monitor and refine the cells within the bioreactor. And if you have to do flow cytometry, that's really not amenable to this closed loop vision of just watching the thing as it's going and intervening without contaminating the product. So this all made us think that perhaps label-free photonics assessment of these cells within manufacturing would be a good way to address many of the current limitations of the process. There's no reagents to use. We're looking at autofluorescence in the cells. The prep time is short. You just look at the cells. You can monitor the cells whenever you want to at any time point. And this could potentially be done in a closed loop system, so you don't have to go in there and sample the cells, potentially introduce contaminants to assess quality. So if we think about where we could intervene in this process, there's several steps. We could check the quality of that original leukapheresis step. We could ensure that those T cells are activated and ready for the CAR transduction step. We could also just assess the quality during expansion to see if the media conditions should change to improve the product. And then we could do a final check right before we release to the patient so that we can determine if the product is meeting release criteria. So I mentioned to you before that T cell activation is required for that CAR incorporation during manufacturing. So we know that quiescent T cells, just circulating in your blood, when they see an antibody, they activate, and there's this huge change in their metabolism. So this is the glycolytic switch I was talking about. And when they become activated, they actually become cytotoxic T cells. So these are the T cells that are going to attack the tumor cells. So this is a well-established thing. Everybody knows this. When you activate a T cell, its glycolytic metabolism goes way up. One way you can measure this is with an oxygen sensor. So this is actually a commercial product. It's called a seahorse, just like the little critter in the ocean. No correlation with anything it measures. I think they just like the little seahorse. I don't know. And they also measure the pH of the media. So this is what we're plotting here, the oxygen consumption over the extracellular acidification. And that's just a standard measure of cell metabolism. So we were wondering if we could measure this huge metabolic switch with just autofluorescence microscopy. So the autofluorescence molecules that we're looking at are NADH and FAD. So actually NADPH and NADH optically overlap. They have the same spectrum and lifetime properties. So we refer to them collectively as that NADPH. So this is just a zoomed in view of a few of the reactions in which NADH and FAD participate. You can see it happens in the cytosol, in the mitochondria, and basically they're taking part in oxidation reduction reactions. So NADH donates electrons to reactions and FAD accepts electrons in these reactions. So if we take the ratio of these two molecules, we're just measuring the oxidation reduction state of the cell. And this is one global measurement of cell metabolism, but it's also very sensitive to shifts in preferred metabolic pathways. So that's just an intensity measurement. So here we're just measuring the number of photons we get back from NADH and FAD, and we take the ratio. You can also measure the time of arrival of the photons. So this is where we do our lifetime measurements. We use single photon counting. So what we do here is we have a short pulse from our laser. So that's what the green is here. We consider that our impulse response function. And then we have a decay time, and this is kind of dependent on what time you measure the arrival of the photon. So you have many laser pulses, and then you measure the arrival for each of these photons. And you don't get a photon for every laser pulse. But eventually, you build up a decay like this, where you assign photon arrival times, and eventually you recover the fluorescence lifetime of the molecule through this decay. So we're measuring the fluorescence lifetime of NADH, and this is because it has distinct lifetimes depending on whether it is free, so it's not donating electrons to an enzymatic reaction here, or if it's bound to a protein and donating an electron to an enzymatic reaction. So the difference here is that when it's free, it is self-quenching, so you can see it folds in on itself. And when it binds to a protein, there's extension of the molecule and less self-quenching. So in this way, we can really measure the free and protein-bound pools of NADH. And it's actually very sensitive to cell metabolism again, but it's also a really robust measurement because it's mostly independent of the number of photons you collect. It really just depends on the time of arrival of those photons. So it's a really reproducible and robust measurement. So for these two molecules, they are distinct in their free and protein-bound states. And so what we're measuring here is their relative protein binding activity. So in these studies, we're measuring fluorescence lifetimes at each pixel, and we're measuring the intensity by just integrating the number of photons under that decay curve to calculate the redox ratio. And since there's two distinct states for these molecules, we're measuring the free and protein-bound lifetime. So we use this 2 exponential fit decay. The short lifetime of NADH, the long lifetime of NADH, and then the short lifetime and long lifetime of FAD. And what you'll see later in the talk is that the fractional component, how much of the molecule is free or bound to a protein, is really important for understanding how the T cells are responding to the biomanufacturing process. So in these studies, we wanted to look at single cell metabolism because we wanted to understand the heterogeneity and the distribution of metabolism and how that might affect function at the end of the manufacturing process. So this is just a cell profiler pipeline that we use to segment single cells. And at the end, what we get is each of these decay variables and the intensity variables, the redox ratio, so several variables for each cell. And we're interested in heterogeneity, so we fit these distributions to multiple Gaussians and then ask how these subpopulations change over time. We use the Akaki information criteria to quantify how many Gaussians and how many subpopulations there are in our sample. And we've done many studies on this and validated that this approach is reflective of the heterogeneity of the sample. So if we think now about what kinds of cells are in that CAR T cell product, there's 2 types. There's the cytotoxic T cells I mentioned before, that's the CD8 ones, and then the helper T cells. And it actually turns out we need both of these to orchestrate an effective response in the patient. So it's not just those cells that are killing the tumor cells, we also need their helper T cells. So we'll look at both of these in our studies. So as I mentioned before, we have a naive T cell. We activate it with a tetrameric antibody, and then we look for a change in metabolism that's reflective of lots of glycolysis. So that CD4 T cells, there's many different subtypes. We'll get into that a little later, but I wanted to introduce them here because they have different pro-tumor and anti-tumor activities. But first with the CD8 positive T cells. So for these studies, we use peripheral blood, so we just get blood from donors, and we isolate the T cells. We have quiescent pools, we have activated pools, and again, we use this tetrameric antibody to activate them, just as they do in the manufacturing process. And then we know that just because we tell the T cells to activate, they don't always activate. So we have to validate that they are actually activated with a surface marker. And in this case, we use CD69. Here we have just some representative images of the T cells before they're activated and after they're activated. And what you might see here is that the T cells expand. So they get bigger, and this is a known feature of T cell activation. You can also see that there's various changes in the lifetimes. You can see here the cytoplasms of the T cells are very small. This whole thing here is actually the nucleus. And then you'll see at the bottom where the CD69 label shows that only a subset of these T cells are actually activated, even though they all look like they're getting big. And then if you quantify the data, you see something very similar. So this is just the features of the donors, which I think were all, very young, healthy people, probably my grad students. So they have a significant change in cell size with activation, but it's not very reproducible. So you don't see the same change in cell size with each donor. And so this is not a good measurement to threshold on to determine activation. Conversely, what we found with NADH alpha 1, so this is the variable that measures the amount of NADH that's in the free state. So it's showing the percent of the NADH that's not actively participating in an enzymatic reaction. And just by eyeballing this data, you can see it's a small change. It's only a 10% change, but highly reproducible. So this is another feature of fluorescence lifetime imaging. These error bars are so small, you can't even see them in most of these measurements. But this means that this could be something that would be worth thresholding on to more robustly determine T-cell activation, which is an important part of the manufacturing process. So the next part we asked was how robustly could we measure activation on a single cell level using these fluorescence lifetime variables. So to do this, we split our data, into training and testing sets, and we used a logistic regression model and then just plotted the receiver operating characteristic curves. That's what you see here. And the endpoint measure we're using is the area under the curve. So that's just a measure of model performance. So how well can we determine whether a T cell is activated or not based on, in black here, all the features, that's all the fluorescence variables, intensity and lifetime from NADH and FAD. It does very well. If you look at just cell size, which, eyeballing it looks like a good measure, but it's not very high performance for classification accuracy. If you look at just this one variable, the NADH free component, it is almost as good as all 10 of the variables altogether. So that tells us that we could perhaps gate on just this one variable and measure T-cell activation really robustly and reproducibly. So that was the T cells from the CD8 pool. If we take all T cells together, that's what we call CD3 positive T cells. The story is very similar. So we see we do well with all 10 features, but we do almost as well with just the NADH alpha 1, so the percent of NADH in the free form. So then we asked, well, what if we just mix up the T cells? What if we take activated T cells, mix them up with quiescent T cells? Can we still identify who's who in these mixed populations? And it's actually very interesting because T cells have quorum sensing. So they actually change their metabolism and their function depending on who is around them. Here again, we see NADH alpha 1 is a really good measure of activation in these mixed cultures. And then if we do the same unbiased classification approach, we again find that the NADH alpha 1 variable does very well all on its own, almost as well as all the fluorescence variables that we measure. So we started to ask a little bit more about how specific this measurement was. If we just look at the T cells in the peripheral blood, some of them are in their quiescent state, so that's the gray curve here. And you can see there's two really distinct subpopulations just circulating in your blood. One that looks more like activated T cells and one that looks more like, quiescent T cells hanging out. And when we started to dig into this, we saw again that the NADH alpha 1 was quite different in these quiescent T cells, depending on whether they were naive or they had been exposed to some kind of antigen and had some memory. So that's what these markers are measuring. So I talked a lot about the CD8 positive T cells because those are the cytotoxic ones. We want those to be robust in our product, but we also really do need these CD4 helper T cells. So there's many subsets in these helper T cells, and so the first question we wanted to ask was whether we could just classify whether a T cell was a cytotoxic T cell or a helper T cell, because it turns out in these CAR T cell therapies, we do need to modify the ratio of helper and cytotoxic T cells to improve efficacy. So this is the first question we asked, and actually for the purposes of visualization, I wanted to show at least once, you can take all of these variables, we had 11 in this study, and project them back onto two-dimensional space. So UMAP here is very similar to something like principal component analysis, except it takes the distance between cells in multi-dimensional space and it preserves that distance and then maps it back onto 2D space. So the goal with a UMAP here is to see how different cells cluster. And so what you see with the clustering here is that it sure looks like the CD4 positive T cells that are quiescent or activated and the CD8 positive T cells that are quiescent or activated cluster somewhat differently in multi-dimensional space. So again, we take a classifier and we ask, well, how robustly and reproducibly can we determine whether a T cell is one of 4 groups in this case? We're asking whether they're CD4, CD8, or CD4 activated or CD8 activated. And if we use enough cells in our training set and we test with, say, about 30% of the remaining cells, we do quite well. about 99% accuracy. That's again based on a logistic regression model. And if we go back to the original variables and we ask what are the most important variables for this 4-class discrimination, we see that the NADH lifetime variables are very important. So all of those studies were actually done with a 2-photon microscope. So it was more of a feasibility study. Are these measurements useful, and in what way are they useful? And we understand that if we want to actually integrate this into a biomanufacturing workflow, we have to change the hardware and the approach that we use so that it can be more easily integrated. So we decided that the best way to integrate with biomanufacturing was to create hardware that would work with a flow cytometer and perhaps would work with an inline monitoring system. So the first thing we really wanted to do was see if we could do this with single photon excitation. We still have to use a pulsed laser because we're measuring fluorescence lifetimes, but we want to be able to integrate perhaps with those systems that are not built for 2-photon excitation. So in this study, we used a 375 nanometer picosecond pulse laser. So again, this is a UV laser instead of infrared laser because we're working with single photon excitation. So we have to be careful about the power levels we use in these studies. We also changed the optics so that our excitation spot size pretty much overlapped with the T cell size. So that way we could just illuminate the whole cell and get all of the fluorescent photons back from that cell one at a time, because that is our minimal measurement. And these are the specs of the laser, the pulse width and the repetition rate. We also wanted to create, decay curves and decisions quickly. So we use these time tagger electronics, and it includes an FPGA. So that means we can then just program the FPGA to threshold based on the NADH alpha 1 levels. And we can send that signal to a sorter using this USB 3 in a time frame that's amenable to actually sort cells in a meaningful time frame. The nice thing about these time tagger electronics, we're not so limited by the count rate because, again, we're looking at autofluorescence, so not a lot of photons happening there. The dead time is helpful too, so we can be really efficient about detecting all the photons. We also have 100% duty cycle, so it's just a lot more efficient way to collect the data. So with this more, cost-effective and hardware that's more amenable for the flow cytometry industry, we just checked with one donor whether we could find, similar classification accuracy with this single photon approach as with our 2-photon approach. So here we just plotted again the short fraction of NADH alpha 1 value, and you can see just visually that the quiescent and activated T cells separate well here. And if we then again do a non-biased classifier with a receiver operating curve plotted here, this is again a logistic regression classifier. You can see that just the alpha 1 value itself performs very well and almost as well as all values together. So this is very similar to what we found in our 2-photon studies. So we're hopeful that these hardware changes could mean that we could actually incorporate this into a flow cytometer. So today I talked mostly about T cells because it's most relevant, I think, to industrial applications, especially in biomanufacturing, given the CAR T cell market. But we're also looking at many of these other cells in blood. So I've had a lot of fun looking at B cells, and actually neutrophils are my favorite because if you look at them, they kind of look like smiley faces. But they're actually real fun to work with because you only have a few hours of time after you take them out of the blood before they kind of peter out. But they're very interesting. So overall, today I talked about applications of fluorescence lifetime imaging for T-cell biomanufacturing. And I think this is a great industrial need because there's many clinical trials right now that are happening both in the US and in Europe, and they could use improved quality control for passing those clinical trials. This could also address the high costs for each of these doses of CAR T-cell therapy, and we're hoping we could intervene to improve the quality of each of these products. So what we found so far is we can use autofluorescence lifetimes to assess T-cells in a label-free manner so that they can be optimized during manufacturing. And we only look so far at activated versus quiescent T-cells, memory versus naive T-cells, and helper versus cytotoxic T-cells. So there's many more specificity that we could investigate in these T-cell populations. So overall, I'd like to thank all the people in my lab who worked on this. I bolded the names of those who really did the bulk of the work. And thank you for listening. And I'm happy to take any questions.
Thank you very much for your talk. I have some questions. The first is lifetime measurement by photon counting still require gathering a large number of fluorescence photons for reasonable statistics, making it a technique potentially slow. How significant is this downside in your case?
Yes, that's a significant downside because we're thinking about integrating this into a flow cytometer and maybe even a flow sorter. So the way we're getting around this is by actually integrating all the photons we get from the cells. So that helps. That means we get the whole volume of photons all at once. And then we're also thinking about using different analysis approaches. So our initial studies showed that the NADH alpha one was super valuable, but we could also use a Fourier transform of that decay and look at that data in phasor space. And that provides us with a little better statistics for separating the cells. So far, that's gained us a few orders of magnitude, several orders of magnitude of speed. But we're not able to actually use commercial flow cells yet because those flow the cells a little too quickly for us. We have to slow down a little bit more.
Okay. Is the activation of T cell the only effect of modifications? Can T cells that have change in their metabolism but do not react properly to cancer cells be modified? And also, could they be toxic?
Oh, yeah. No, that's a really good question. And lots of the people we've been interviewing in our market research have been asking us what we think we're sensitive to.
Okay. Does not T-cell photosensitivity affect further modification of cells as a result of their imaging?
Yeah, that's a good point, because since we moved from two-photon excitation to single-photon excitation, we're thinking a lot more about viability of the cells, especially as we're measuring them with a 375 nanometer laser. So what we're doing is just trying to reduce the power levels, and then we're checking for viability after we image. And so far, we know we're not killing the cells, but the question is, how are we affecting their function? And so we have to dig a little deeper to understand if we're metabolically changing them or changing their function. But so far, we haven't seen any indications that we're hurting them. I'm sure there's something happening, and we're going to find it, but we don't know yet.
Can you damage a cell by trying to excite autofluorescence, for instance, for example, by parasitic absorption?
Yeah, so we have, again, I mean, there's heat shock proteins, which you can see changes in their expression after you image them. But otherwise, we see no obvious changes in cell function, definitely not changes in cell viability. That's the easiest thing to measure. Are they alive or not? And we're not seeing huge changes in function yet, but I think it depends on the power levels you use. So if we were to increase those power levels or change the wavelengths, those thresholds can change in terms of viability and function of the cell.
Thank you. I have the last question concerning the status of your technique at the level of hospital evaluation. Can you comment this? Is it experimental only, or you started the real patient evaluation?
Yes. Well, the CAR T cell therapies are approved and being used in patients routinely now. We are working with companies that are developing new CAR T cell therapies to optimize those processes. So our technique is still used in the research space to develop new protocols for CAR T cell therapies. So we think this particular technology is most useful in the preclinical phase rather than the already FDA approved phases. So yes, we're testing them with CAR T cell manufacturing, but in the preclinical phase. Yeah.
Thank you very much. Thank you again for the talk.
Thank you.
And now the second session is closed now, and we have a short break. And the third session 3 will restart at 5.
Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin. Zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Światło to jest niesamowite zjawisko. To jest podstawowy składnik materii całego wszechświata, który tak naprawdę spaja wszystkie atomy, molekuły, wszystko co znamy. Światło definiuje czas i przestrzeń. Jest zupełnie niesamowitym czynnikiem, który my jako ludzie możemy odbierać bezpośrednio za pomocą naszego wzroku. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. W tym właśnie zajmuję się ja i mój zespół, próbując oswoić światło i zastosować je do czegoś praktycznego.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin, więc z łatwością zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Wszyscy moi znajomi uważają mnie za pewnego rodzaju magika i poniekąd jest to prawda, bo w tej pracy łączymy różne elementy takiej zaawansowanej techniki optycznej, wyrafinowanej obróbki danych, do tego szczypta inżynierii, żeby tworzyć urządzenia, które poniekąd są magiczne, bo pomagają diagnozować choroby różnego rodzaju, które normalnie nie są widoczne gołym okiem.
Nauka obok sztuki jest jednym z najważniejszych aspektów działalności człowieka. Sztuka może leczyć duszę, ale nauka może leczyć ciało. My zaczynamy od oka.
Lasery, modulatory, mikroskopy i inne urządzenia to jest dla mnie fascynująca zabawa. Eksperymenty naukowe, mimo że często są bardzo zaawansowane, są do ogarnięcia przez jednego człowieka. Teraz pracuję nad taką zaawansowaną techniką obrazowania ludzkiego oka. Mam nadzieję, że ta technika będzie kiedyś stosowana przez lekarzy, wspomagając wczesne wykrywanie różnych schorzeń wokół i będzie techniką nieinwazyjną, to znaczy jak najbardziej bezpieczną dla pacjentów.
I like building microscopes, but as any other instrument, it has its own limitations. So my job is to improve the performance of a microscope. This also means that what I'm doing day to day hasn't been attempted before, which could sometimes be challenging, but always exciting.
My dreams are to finish my project, which is really very challenging, to study about the small growth of the tumors and do something to understand the basic biological and physical process beyond this, to understand how they are really developing and have like a good pharmaceutical drug to cure it.
Pracuję nad nowymi metodami obrazowania, które zrewolucjonizują te metody, które mamy obecnie w mikroskopii, czy też generalnie w kamerach.
Fajnie eksperymentować z ludźmi, dla których rzeczy niemożliwe nie istnieją. Myślę, że najlepsze słowa opisujące pracę u nas w zespole to mierz wysoko i sięgaj celu.
Pod skórą, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Jesteśmy blisko tego, widzimy już światełko w tunelu, jesteśmy coraz bliżej, ale to jest początek drogi.
The cornea is the most external lens in the eye. Along with the crystalline lens, it projects the images of the outside world onto the retina. The cornea is a transparent dome, and its structural integrity relies on finely interleaved collagen fibers. The regular shape of shaped or surgically open. These conditions are highly prevalent, such as myopia, that affects 30% of the population in Western countries and 90% in some Asian populations. Presbyopia, the age-related loss of dynamic focusing capacity, which affects 100% of people older than 45, and cataract, the loss of transparency, which affects 50% of the population older than 65. In corneal refractive surgery, used to correct eyes' refractive errors, a laser is used to sculpt the cornea into a different shape. Alternatively, new techniques are being developed where biomaterials or tissue is implanted in the cornea to correct presbyopia. In cataract surgery, an intraocular lens is implanted through an incision that needs to be made in the cornea. While all these treatments rely to a larger or lesser extent on the mechanical response of the cornea, today there is no clinical instrument that either detects corneal mechanical abnormalities or can help in predicting the mechanical response to surgery. i-POB, a project funded by the European Commission Horizon 2020 program, addresses this unmet medical need. i-POB has gathered a reputed multidisciplinary group of experts in academia, industry and clinic to deliver and demonstrate a new clinical instrument which will put Europe in the ophthalmic industry and strategic position in the field. World's most prestigious ophthalmology clinics, Moorfields Eye Hospital and Instituto Oftalmológico Fernández Vega, both with flows of thousands of patients per day. The multidisciplinarity of the consortium will ensure an efficient translation of the front-end laboratory designs and prototypes into a viable instrument that will be tested in pilot clinical studies with patients. i-POB, bringing light-based technologies to improved diagnostics and personalized surgery.
Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin. Zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem.
The cornea is the most external lens in the eye. Along with the crystalline lens, it projects the images of the outside world onto the retina. The cornea is a transparent dome, and its structural integrity relies on finely interleaved collagen fibers. The regular shape of the cornea is, therefore, the result of its biomechanical rigidity. However, the cornea is not a piece of plastic, and different corneas may respond differently to mechanical stimuli. In several pathologies, such as keratoconus, the cornea weakens locally, resulting in corneal bulging and vision distortion. Keratoconus affects 1% of the population, and treatment requires implanting a supporting structure inside the cornea, intracorneal ring segments, or stiffening the cornea, instilling a dye and irradiating with light, a technique called cross-linking. There are other ocular conditions in which the cornea is reshaped or surgically open. These conditions are highly prevalent, such as myopia, that affects 30% of the population in Western countries and 90% in some Asian populations. Presbyopia, the age-related loss of dynamic focusing capacity, which affects 100% of people older than 45. And cataract, the loss of transparency, which affects 50% of the population older than 65. In corneal refractive surgery, used to correct eyes' refractive errors, a laser is used to sculpt the cornea into a different shape. Alternatively, new techniques are being developed where biomaterials or tissue is implanted in the cornea to correct presbyopia. In cataract surgery, an intraocular lens is implanted through an incision that needs to be made in the cornea. While all these treatments rely to a larger or lesser extent on the mechanical response of the cornea, today there is no clinical instrument that either detects corneal mechanical abnormalities or can help in predicting the mechanical response to surgery. i-POB, A project funded by the European Commission Horizon 2020 program addresses this unmet medical need. i-POB has gathered a reputed multidisciplinary group of experts in academia, industry and clinic to deliver and demonstrate a new clinical instrument which will put Europe in the forefront of personalized diagnostics in ophthalmology. The partners of this highly international consortium are Project Coordinator, VO Lab at the National Research Council, a pioneer group in optical imaging eye diagnostics. Academic partners, Polish Academy of Sciences and the National University of Ireland Galway, both world leaders in biomedical optics and photonics, and University of Liverpool, experts in corneal biomechanics. Two Eyes Vision, Oculus, Optimize and iRock Science, all international companies selected for their unique technical expertise in the ophthalmic industry and strategic position in the field. World most prestigious ophthalmology clinics, Moorfields Eye Hospital and Instituto Oftalmológico Fernández Vega, both with flows of thousands of patients per day. The multidisciplinarity of the consortium will ensure an efficient translation of the front-end laboratory designs and prototypes into a viable instrument that will be tested in pilot clinical studies with patients. i-POB, bringing light-based technologies to improved diagnostics and personalized surgery.
Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin. Zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem. Światło to jest niesamowite zjawisko. Obdarzeni jesteśmy możliwością kontroli światła, możliwością sterowania tym światłem i używania go, na przykład do obrazowania, do tego, żeby w komputerach mieć obraz naszej tkanki. Tym właśnie zajmuję się ja i mój zespół.
W naszej grupie zebraliśmy specjalistów z bardzo różnych dziedzin. Zajmujemy się zagadnieniami z pogranicza biologii, medycyny, farmakologii czy fizyki laserów.
Cały czas staramy się rozwijać nowe metody, a jednym z nadal nierozwiązanych problemów jest problem, jak zobaczyć komórki w żywym organizmie. Naszą ambicją jest rozwiązać ten problem.
The cornea is the most external lens in the eye. Along with the crystalline lens, it projects the images of the outside world onto the retina. The cornea is a transparent dome, and its structural integrity relies on finely interleaved collagen fibers. The regular shape of the cornea is, therefore, the result of its biomechanical rigidity. However, the cornea is not a piece of plastic, and different
Welcome back after this short break. We have the last session today with three fantastic talks, and all three talks will be made by people who are really experienced in industrialization, especially our first speaker, Eric Backlund, who is currently CEO of Translational Imaging Innovations. But he, in past, he co-founded Bioptigen, and he was for a long time CEO of Bioptigen, that beautifully exited in 2015 for Leica Microsystems. And he also had experience in work with Sumitomo Electric, Alcatel, and Corning. And we will have his excellent talk right now. Eric, here.
Thank you very much.
The floor is yours.
Thank you so much. Thank you for inviting me to come to this really important conference on the industrialization potential of optics and biomedicine. Thank you for the introduction. The title of my talk is Romancing the Startup, Starting the Entrepreneurial Journey on the Right Foot. My objective today is to try to remove some of the mythology of starting an entrepreneurial journey, but while keeping the romance in the process. Oops, excuse me, got to get my clicker back working. Okay, first I'm going to give you a little bit of my background by way of academic genealogy, because it will lead to an interesting set of circumstances. First, I completed my PhD under Bob Boyd at the University of Rochester, working on acousto-optic interactions in optical fiber, and I wasn't bright enough to see the future in photoacoustic biomedical imaging. Bob got his PhD from Charles Townes, Nobel laureate for lasers. If we take his steps back a couple of steps, his terminal great-great-great-grandfather of academia is Albert Michelson, who, in addition to eliminating the ether from our view of the universe, invented the Michelson interferometer, which is, of course, the core component in current OCT systems. So therefore, I was destined to be in the OCT field at some point. Before I did my PhD, I did a master's degree in near-field microscopy under Michael Paisler at North Carolina State University. And Michael's genealogy goes back quite a bit longer, in fact, many centuries. And it ends with, oh, come back here. Excuse me. It ends with a young gentleman named Nicholas Copernicus. So my genealogy brings me right back to the Nicholas Copernicus University. And so I'm very proud to be here today. So there's a lot of romance in startups. And for those of you who may be too young, romancing the startup is a reference to Romancing the Stone, an entrepreneurial journey movie in the early 1980s. But let's start with a brief definition of what entrepreneurship is. So a definition that I like is that entrepreneurship is a pursuit of opportunity beyond the resources you currently control. And I think that's an important point to make. So when you start out on your entrepreneurial journey and step out of the lab, you are going to make something from almost nothing. As Maciej mentioned, my entrepreneurial journey in this space is centered around first Bioptigen, a company that I co-founded with Joe Izat of Duke University in 2004. And this was at the toe of the SDOCT revolution. And we focused on building systems that would have the best image quality and seeking applications that would benefit from that image quality. That led us to the dubious distinction of having the best mouse imaging system in the world and quite literally because MD, PhD saw we could image small mouse eyes. They asked us to do pediatric imaging. We built the first handheld ophthalmic imaging system and had that FDA cleared for even premature babies. So the Invisu is still the only pediatric OCT on the market, sold by Leica. And because babies are inherently uncooperative, many of them are imaged in the OR, and that brought us into the OR. And so clinicians with their surgeon colleagues asked us to build intrasurgical OCT and integrate it with microscopes, which we did. We were funded off of a lot of grants from the US SBIR program. We received 4 FDA 510K clearances, and we were selling in 30 countries before we were acquired by Leica Microsystems to advance the intrasurgical imaging opportunity in 2015. After integration with Leica, I left to do new things. And so I'm continuing the entrepreneurial journey in spite of myself, and I've formed Translational Imaging Innovations. And our vision is to unleash the power of the eye to transform medicine. The bottom line is that while we get such beautiful images from all of our imaging systems in this space, we're in the era of big data and artificial intelligence, and we need workflow and methodologies to extract all of the beautiful information, the latent medical information, all of these images. And this is what we're doing in TII. So part of the mythology of startups is this unicorn, the mythical unicorn. And so investors and entrepreneurs, everybody wants to be a unicorn. Unfortunately, sometimes all we do is end up with a donkey. So I want to try to provide you some guidance, at least to get you started, so that you have a greater probability of becoming a unicorn and not a donkey. I'm speaking largely to a physics community, one way or another. A few years ago, the American Institute of Physics did a study of entrepreneurs, physicist entrepreneurs. And as you can see, a large proportion of us who take the entrepreneurial path end up using our broad skills in instrumentation and specifically in medical devices. So it's not a surprise that many of you are interested in this pathway. CB Insights recently did a study on why startups fail. And I think it's instructive to start with the discussion of why we fail so that we can try to head off these failure modes. So the first 5 reasons: there's no market need, we run out of cash, we don't have the right team, we get outcompeted, or we have pricing and cost issues. The next 5 are subsets of that. We produce a user-unfriendly product, we have a product without a business model, we have poor marketing, we ignore our customers, or our product is mistimed. These can be summarized to the following categories: market, team, the product, our funding, and our execution. So let's build the right foundation to get our startups off the ground. First, we need to understand our market. We have to build an appropriate founding team. We have to define our product. We have to secure the technology rights so that we can build our product. We have to secure funding, and we have to execute. So I'm going to take these topics now and walk through each of them one by one. So first, it's important to understand our market. It's really important to understand that you are not your market. We get enamored with our technology and the response from our colleagues and citations and papers. But in spite of that, we need to take a step out and think more broadly about what a market is. And I'm going to use this definition as a guidepost. Your market is a collection of potential customers who will share a common pain point that they're willing to pay for to solve. It's important to understand how big your market opportunity is, and two simple metrics. One is how many customers share this common pain point, and second, how much will they spend to ease their pain. So it's really critical before you get started to have a sense of what the market opportunity is. The market opportunity matters because there is risk in startups. Investors really like to back large opportunities that are worth the risk. Having an understanding of your market, now it's important to build a team. It's important to consider the skills of the team you're going to bring forward, whether it's you, 2 people, 3 people, or 5 people, and that you have complementary skills to bring together all of the stools for the chair that you need to build a business. And the first question is, do you have a member of the team who can bring business skills to complement your technology skills? The next important question, which is less obvious in practice than it may seem at the beginning, is make sure your team shares a common vision. Your CEO, whether that's you or someone you bring to lead your team, is the owner of the vision. But for a team to attack all of the issues that are in front of them in a startup, you have to share this vision. You're heading into the Wild West in an entrepreneurial venture, and you're not going to know everything or have the skills to do everything you need. So you need to have and use a network of trusted advisors, and those trusted advisors will be people who've been through this. They'll be financial people and legal, patents, etc. But you also need lead customers among your advisors, and those customers should share your vision, but do so in a way where they are willing to provide you honest feedback and help you steer your way to a proper execution of your vision. The teams matter, and we hear often that investors back teams that they believe in because teams are going to have to make a lot of decisions, execute, and navigate their way through the entrepreneurial matrix. There are a couple of pitfalls related to your founding team that I'd like to discuss briefly with you. First, while you may believe that you have the same vision in common, there are a lot of decisions to make, and I think it's important for founders to start with a founding agreement and put down on paper their expectations for the venture going forward, their roles in the venture, and how they will evolve with the venture. A critical point is establishing your share of equity among founders. I've seen many ways of doing this, equal shares or a senior member of the team commanding a greater share of equity. It's important to realize that whatever you're starting with, the contribution of those who execute and carry forward is what's going to make the business a success. So make sure that you set up equity in a way that rewards those who do the execution. At the same time, founders don't always agree forever. So it's important that you have vesting in your shares. That is, ways to call back shares if a founder prematurely leaves the company. And so consider restricted shares and options, and not just the raw issuance of shares in your company to your founders. Remember that founders are married to each other, and they're married to each other for the sake of the business. The business is the child, and founders are the parents. But we also know that not all marriages last. So build a great founding team, but protect that team and protect the assets of this marriage. You have your market vision and team. Now you need to have your product. Make sure your product addresses the market pain. What you built on a benchtop in the lab isn't going to be your end product. You're going to learn from your customers, and you need to make sure that you are turning your knowledge of the technology and the physiology to the market pain. You want to make an impact. That's why you're in biomedicine. Make sure you're developing a product that's going to make an impact for your customers. And of course, we're all targeted at improving outcomes for patients. You need to make sure your product is clearly differentiated. You will be competing. I think when we have a new innovation, sometimes we think we are so innovative that we don't have competition. That's never true. You will have competition near and far to what you do, and it's important that you are differentiated, you can spell out your differentiation, and that your customers understand why they want to buy from you rather than stay with their present mode of activity or a competitor. And then make sure the market is ready for your solution. So I'm speaking to a group that is in the laboratory. You are doing forward-looking, cutting-edge research. Sometimes the market, for various reasons, is just not ready to make a change that your solution would require. So be careful and be honest about the market readiness to adopt your solution. In that sense, timing matters. And keep in mind that there can be barriers to adoption, even of very great ideas. So that should be part of your consideration of the business you're going to form. In addition, you're building a product that is going to intersect with how your customers get their work done, whether that work is research or clinical diagnostics or a therapeutic intervention. Your customers have a workflow. It's your job to uncover that workflow and make sure your product fits into your customer's workflow. In doing that, you may have to make sure that you design a product that your customers love. Particularly today, where software tools have made it relatively easy to design beautiful and user-friendly interfaces, there is no excuse not to create a product that customers will love. And finally, you have to build a business. So you have to build a product that you can manufacture and sell profitably. So you have a cost side to consider and a price side to consider. Unlike social media, where you can build a network and lose money for decades and keep your investors happy, that's not so much the case in our space. So you have to make sure you can build a product and sell it profitably to your customers in the market you're targeting. So in our era, the message I want to leave you with is that design matters, and make sure that you're getting feedback from your customers early and often. You need to make sure that you have the rights to your technology. Likely you are coming out of an academic institution. You need to make sure you have the freedom, not just from your academic institution, but from the competition, the patent landscape, that you have the freedom to operate with your technology, and that you can secure a license to your technology, likely from your institution. A lot to discuss on licensing, but put a big red star there. It's important that you start off with appropriately scoped and priced licenses for your technology. But your initial licenses are only the beginning. So in my experience, you will generate more intellectual property from solving problems specific to your market and your customers' needs. And you need to build that IP inside your company and exclusive of your starting institution. Patents do matter. They matter for creating barriers to competition, and they matter at your exit, if you're searching for an exit. So make sure to build a strong and credible intellectual property throughout your journey. You need funding. The key message I want to leave you with here is early stage funding is difficult. Be prepared to bootstrap until you have very strong market and clinical validation. Take advantage of incubators and accelerators in your area and the new class of online incubators to help you map out your business and think through the entire universe of what you need to think through as a business operator. Your early stage money has to come from you, from grants. You can get seed stage funding from friends and family and angels. Make sure to do that with legal advice and under appropriate legal and fiscal terms so that you are fair to all of your early investors and are credible to your next round of investors. I do want to stress that early stage funding is really challenging. It's challenging in our area. Therapeutics and devices are quite different, and hardware devices really need a strong degree of validation and market assurance to get funding. And we all hear about VCA rounds. VCA rounds, when you're ready to scale, they require clear market validation, clear evidence of customer acquisition for medical devices, regulatory clearance, and they need revenue. And today it's not uncommon to see VCs requiring $2 million in revenue before jumping into an A round. So you've got a lot of work to do before you get to that point. My last message is to execute. I see this frequently. We've got to get you out of academic mode fast. A business and a research environment are not the same. Learn and adopt agile and lean technologies to manage your development cycles. And with a little bit of perhaps controversy, I would say implement design control early. Design control leads to a bit of bureaucracy, but what it requires is careful enumeration of your requirements, execution to your requirements, testing as you go along, and it will lead you to a positive regulatory output faster. And if you don't implement design control, my experience is you will go backwards more than one time. So invest the time early on to get your design control systems in place. And finally, you need to get clinical validation. And so for a lot of the early technologies and some of the beautiful technologies that you're hearing about in these next 2 days, where the physics, the optics, the physiology is great, it's really critical to get clinical validation as early and as statistically strong as possible, and listen to that clinical validation and steer accordingly. My message is, if you're still really doing research, stay at your uni, stay at the university. Don't come out until you're ready to start a business. When you're starting your business, be rigorous, design milestones, and hit them. Hit them for yourselves and your team, and you'll be in a position to hit them for investors and your customers. You will need to navigate. Things will change. Your understanding will change. Navigating is steering around icebergs, but leading to the direction that you've already established. Sometimes you want to change your endpoint, and in that case, you pivot. Navigation is necessary. Pivoting may be necessary. Pivot if necessary. So to summarize, go after unmet needs in a big market. Address the pain point of your customers with a differentiated solution. Build a complementary team and protect the marriage. Build a product that customers love and will buy. Create moats and barriers to protect your space. Secure the right capital at the right time. Execute, navigate, and grow. And hopefully, with these foundations, you won't be a donkey, but you'll be the next unicorn in biomedical optics. I'd like to acknowledge my teams at Bioptogen and Translational Imaging, and thank you for listening. I look forward to any questions. Thank you very much.
Beautiful, Eric. So thank you for this talk and this like really exact pinpoints that we can just put on our walls and see it every day, read it every day, every morning to do what should be done. We have quite a long list of questions actually, but there is no time for all of them, but they should be somewhere in a chat or a Q&A tab. But I will ask some. So thanks for the inspiring documented and structured steps to approach entrepreneurship. When do you think that we should start training our engineering or physics students on considering enterprise activities? As early as the first year or the end of the studies, or continuously mention the topic to our students over the years?
In my personal opinion, I think the concepts of product development and let me say it this way, product development should be taught early and even at an undergraduate level. So I watch a lot of like design courses at the undergraduate level. I think for groups that have design courses, those should be maybe recalibrated to what the real world looks like. That'd be one suggestion. I think, at the graduate level, I think people have a sense of whether they want to go academic or PhD, and I think resources to understand how to think about a product development, regulatory issues, and business should be available as early as possible. It is a mind change that has to be made. There's an impedance mismatch between the environments. So for people who are interested, I think internships would be great, and any opportunity to learn the techniques of actual commercialization and industrialization would be very valuable earlier on. Mm-hmm. I think that can lead to faster translation of the technology, which is why I call my company Translational Imaging Innovations.
Okay, another question is, what is your advice on market analysis? How physicists should approach this? Seek advice somewhere, pay them for market analysis, or what to do in this case?
I think this is really hard. This is the hardest piece, and it's hard for me. Every time I do it, it's very hard. One is learn to do a little bit of research on your own. So the great thing is we have a great internet. Ask questions, talk to people who do investment or think about companies, ask them what questions they want to know. And get on the internet and just use your search terms the same way you would search for technology information, search for market information, and build a knowledge set. I find particularly on innovations, it's very hard to define the market. It's hard to come up with that statement of what you are doing. And I don't have a silver bullet. I don't recommend paying people to do this for you. You have to understand your market. So every time I have paid, I have been disappointed. At some point, you do need a business associate, somebody who's interested in taking the journey with you. But until then, use the internet, search, test your assumptions against your colleagues who are technical and against other people you know who have more of a business mindset. But do it yourself.
Okay, and maybe last question. Is the market ready for your solution? What about creating a market? How risky is this approach?
So if you look at a matrix of how novel, four-square matrix, how novel is your technology and how new is the market, the hardest box is new technology and a new market. Forget it. Don't do it. So, there's always an exception. So if you've got the sort of personality of Elon Musk or Steve Jobs, do whatever you want. Mm-hmm. Most of us aren't there. So my suggestion is new technology and an understood market is your best opportunity. Defining a new market is hard to get investors to understand, hard to get customers to understand. With that said, I do think success is on the convergence of market trends. So you may intersect a market that your customers don't think about. That's kind of a different story. And but what I would say is get a little experience under your belt first. And so take your new technology into a market that your customers can understand first.
Okay, Eric. So thank you so much for sharing with us your thoughts and your really fantastic experience in this field. So this is really absolutely unique. So thank you very much, and please follow all questions in chat. So people are very interested in this and having your advice.
Anyone's welcome to reach out. So we'd love to hear.
Okay, thanks
you. Thanks very much.
Bye bye. Okay, we can move to another talk. Actually, when we think about diagnostics and clinical instruments, we must face somehow Zeiss Meditech company. And we have today excellent opportunity to hear Mary Durbin, who is the Director of Clinical Research and Analytics Development at Carl Zeiss Meditech. And she works for 14 years in image analytics, and recent enormous developments in OCT instrumentation and software in commercial systems is largely due to Mary and her team, R&D team in Zeiss.
My name is Mary Durbin. I am Director of Clinical Research and Analytics Development at Carl Zeiss Meditech. Since the conference is about industrialization potential of optics in biomedicine, I am going to discuss the efforts we made over the past several years to industrialize quantification of optical coherence tomography angiography, focusing on what we have done to demonstrate its validity, since these methods are common to any new quantification that someone might want to introduce. So optical coherence tomography is an interferometric imaging technique that uses low coherence light. It has been described as ultrasound, but with light. It is particularly suited to ophthalmic imaging. The basic unit of the OCT signal is usually an A scan, which basically would run from the top of this structural image to the bottom of the structural image. But you get a B scan by scanning it across the eye. A set of B scans can represent a three-dimensional sample that is a virtual biopsy of the retina. OCT angiography was developed later when researchers started taking advantage of the complex signal and comparing B scans in repeated fashion at the same location. Comparing such B scans could be done in either complex space, phase space, or amplitude space. This comparison essentially shows you when there's anything changed in the B scan. So if you run the B scan twice in the same place, everything should be the same. Anything that's moving is not the same. You have to subtract out things like bulk motion, and that's a technique that you need to apply. But then what you're left with is anything that might represent motion in the eye, specifically erythrocytes moving in the blood vessels, which you can see here and here. This is just a false color overlay of the flow signal on top of the reflectivity signal. But visualization of OCT angiography is best done in en face. And en face basically means looking from above. So if you see here a schematic of the eye, if you segment the upper portion, the inner limiting membrane, and you basically sum 2/3 of the values of your flow volume below that red line, then you'll get the superficial capillary plexus. But for instance, if you sum below the RPE, which is this blue line here, then you get the choriocapillaris. You can see that you get very different vascular structures in these two different parts of the eye, and they tell you about different aspects of the eye. So if you want to look at the layers we actually care about in the retina, particularly we're going to be talking about the superficial retina, you can also look below that at the deeper retinal capillary plexus, and that has, again, a slightly different structure. It's connected to the superficial retina. So what we're going to tend to find is that the superficial retina is really the primary thing that we're going to look at. You can also look at the avascular retina, where you don't expect to see anything, at least in a normal eye. So it's blank in a normal eye, but if you see invasions there, then that can be a sign of pathology. You can sum these together to get a full retinal image as well. But then what are you going to do with this? So diabetic retinopathy leads to capillary closure. And you can see this in these more traditional methods. Dye-based angiography is shown on the right-hand side, where you inject the person with a fluorescein dye, and then you can watch it traverse the eye, and you can see areas of ischemia like this dark spot here. But of course, that requires an injection. You can also see evidence of abnormalities in the vasculature in a traditional fundus image. You see areas of edema and exudates that result from edema, and you can also see vascular abnormalities, but not at the level of detail that you can see with OCT angiography. So OCT angiography can be used to visualize areas of capillary non-perfusion. So what we're showing here is one of our Plex Elite images. It's a swept source form of OCT using a swept source laser, but it has a wide field of view, and you can see these areas of ischemia out here. But even if you zoom in on the foveal avascular zone, you can see that it's way more avascular than it should be. It's become quite ischemic. So you can visualize these things, but then the next thing you're going to want to do is to quantify them. So switching over to our spectral domain device, the Cirrus with the Cirrus Angioplex, this is showing you a report from the Cirrus Angioplex showing detailed, basically a density map overlaid on the microvascular image that you get from the device, together with other images that help you interpret it, and these quantitative numbers. So you can objectively measure the microvascular density, and that's inversely related to capillary closure, which is a feature of diabetic retinopathy. And we offer both vessel density and perfusion density. They're two different ways of looking at the microvasculature, and let's talk about the details of that now. So the perfusion density is based on a binarized image. So you take the microvascular image and you binarize it. Either something is above the threshold and it gets 1, or it's below the threshold and it gets 0. Now you have to do some additional computer vision techniques on top of that, filters and stuff to get some connectivity. But overall, you're basically turning your grayscale image into a binarized image. And then you can express the percentage of ones in the overall area, so that ends up being a ratio. So this is the perfusion density, and it represents the potential perfusion in any given region. Alternately, you can take this binarized image and you can skeletonize it. And once you skeletonize it, you can ask how many lengths of vasculature are there in any given area. So you're basically looking at a length metric, millimeters, divided by an area metric, that is millimeters squared. And this is going to be important to pay attention to, because we call this one vessel density and this one perfusion density, but in the literature, people are not super clear on which is which. And I find that the best way to know what someone is using is to look at the units that they're using. So if the units are per millimeter, then it can be compared to what we call vessel density. And if it's a ratio, then it's more likely to be based on a binarized image and to be what we call perfusion density. But let me go into a little bit more detail and show you this by zooming in on these areas of the image. So you zoom in here and you can see that where you had a large vessel, a medium vessel, and a small vessel, these are all a single pixel wide in this skeletonized image. So you can see how if you do quantification based on this image, it's going to account for the size of the large vessels, and a medium vessel will count for more than a small vessel. But if you look at this one, all vessels count the same. And so these are measuring different things in the eye, and they may have different value depending on what disease you're looking at. And then just to get at some of the more details of what you can do, how this quantification works is going to depend on the resolution of the image. So we offer quantification on 2 types of image. One of them is the 3 millimeter by 3 millimeter scan, which has 245 clusters of 4 repeated B scans, where each B scan has 245 A scans. So the spacing between any given unit here is going to be 12 microns. Alternately, we have the 6 millimeter by 6 millimeter scan, which in order to fit into the kind of time window that we feel is useful for this kind of imaging, we're using 350 clusters of 2 repeated B scans, where each B scan has 350 A scans. This leads to a 17 micron pixel spacing. So this one is less densely sampled than this one, and that's going to affect how well you can quantify it. Once you have quantified things, then you want to summarize that quantification information so that you can report it out in a small number of parameters. But realistically speaking, there's really still quite a few parameters. So, we are using the grid that came out of the early treatment in diabetic retinopathy study, which consists of basically a 1 millimeter diameter central field, a 3 millimeter diameter split into 4 sectors, and then 6 millimeter diameter split into 4 sectors. So this means that you've got 9 parameters for the 6x6 scan, 5 parameters for the 3x3 scan. We've discussed that there are at least 3 different layers that you could consider quantifying: the superficial, the deep, and the combination of the 2 of them. And then we've described both vessel density and perfusion density, which doesn't even bring into the question other metrics that other people have proposed, like fractal dimension, tortuosity, etc. So you've got this proliferation of parameters, and you need to figure out, well, which ones matter. And so that's going to be the real focus of what we want to talk about here. So how to select and validate parameters and interpret the results. So we're going to have clinical considerations and regulatory considerations. In the clinic, what you care about is whether it maps to disease. Does it have diagnostic efficacy? Can you detect the disease with it? And can you monitor it by knowing what is real change? So we're going to study this with cross-sectional studies where we do a receiver operating characteristic analysis. But you also need to know what is real change, and we're going to study that with a repeatability and reproducibility study using analysis of variance or ANOVA analysis. But then there are also regulatory considerations. The FDA recently introduced a pilot program with the goal of making consistent the types of studies people do to support OCT and OCTA introductions. So they care about accuracy. So our first attempt to look at accuracy was to compare to what the doctor saw, what the doctor would trace on the image. And they did not really like that. They wanted to see phantoms. So I'm going to show you some evidence from a physical phantom and from a digital phantom related to the accuracy of what we're detecting. And the FDA is also very interested in precision, but we're already going to look at that with our repeatability and reproducibility studies, but they have some ideas about how we should do those. So let's start with diagnostic efficacy, because that's where, if you don't have that, you don't really have anything. So can any given metric be used to detect disease? We're going to look at this with cross-sectional studies. So we did a study with Professor Cunha-Vos at i-POB, looking at 50 diabetic retinopathy eyes and 50 age-matched healthy controls. Using, again, a diagnostic efficacy study, receiver operating characteristic, which basically plots the sensitivity of a given metric against the inverse of the false positives. So the gold standard in this case is the diabetic retinopathy severity score based on a reading center grading of fundus images. And so over here, you see some of the results of this study for at least the 3x3 scan. So the vessel density we found was the best metric. The receiver operating characteristic is best when it's basically, the area under the curve is 1, when it goes straight up and goes straight over. So everything that's more up in this corner is better. So the vessel density was the best metric that we saw. The perfusion density was still acceptable from a diagnostic perspective, but not as good as the vessel density. And the FAZ area turned out to have no efficacy at all. It basically maps along the straight line, which is the same as a coin flip. And we found that the superficial retinal layer densities were better than the deeper retinal layer densities in terms of their capabilities for diagnosis. That was what we found. Not everyone has found that, but and then not shown here, we definitely found that the 3 millimeter was better for diagnostic efficacy than the 6 millimeter. So in conclusion, at least from this study, measurements of vessel density in the superficial layer of the inner ring of the ETDRS grid in a 3x3 scan led to the best ability to distinguish disease from normal. But we still need to know about the repeatability and reproducibility. So we did a prospective clinical study looking at normal eyes and eyes with diabetic retinopathy. And we did this using a design proposed by the FDA, wherein you have 3 devices and 3 operators. Each operator is assigned to a single device, and every subject is imaged on each of the 3 devices by the assigned operator, and they are imaged 3 times on each device. So you end up with 9 measurements per subject, and you can use the analysis of variance to figure out the components of variance that contribute to the measurement variability. And you want to do this in subjects without any diseases and in subjects that have the disease you're interested in. In this case, retinal disease that affects the vasculature of the eye. So we looked at diabetic retinopathy and retinal vein occlusion, and we tried to have a range of severity that went from very early diabetic retinopathy to proliferative diabetic retinopathy, so that we were studying the full range where this might be used. And the results are basically, again, there were quite a few results, but in the end, you're trying to look at the repeatability standard deviation and the reproducibility standard deviation, where the repeatability standard deviation is the standard deviation of the measurement under conditions where nothing changes. You have the same operator and the same device. Whereas the reproducibility, you might change devices or you might change operators. And of course, that's the more realistic scenario. So this is the the important one to look at it. And you can divide the reproducibility standard deviation by the mean of the given measurement to get the coefficient of variability. And in the case of, let's say, for instance, the central subfield where the foveal avascular zone is, that's actually very variable. And so we found coefficients of variance of 11 and 12%. So that's pretty high. Whereas all of the other metrics for the 3x3 scan were between 4 and 6%. And that's a much more reasonable variability for monitoring things in a clinical situation. So our takeaway from this is that for at least the 3x3 scan, both vessel density and perfusion density had good reproducibility and could be used, but not in the central subfield. So just to summarize that, the best parameters to pay attention to are the vessel density in the superficial layer of the inner ring of the ETDRS grid in a 3x3 scan. And from the same study, we could look at what the values are typically in a normal eye and typically in diabetic retinopathy, at least in the diabetic retinopathy that we studied. And then how much is real change? About 2 per millimeters in the vessel density in normal eyes. And it's a little bit worse because often the variability is worse in diseased eyes, and it's 2.6 per millimeters in diabetic retinopathy eyes. But this won't be enough for us to get clearance to market this product. And it's not enough. We need to demonstrate that we're measuring something that's at least reasonably accurate. So in the FDA pilot guidance, they explicitly say if the OCT device features quantitative vascular parameters, then you need to do measurements in a series of phantom images of known content to serve as a reference. So I'm going to show you some stuff from that. So we asked Ricky Wang, and he assigned a postdoc in his group, David Way, to create these microfluidic channels that they placed in front of both our device and a device that they made, where you basically pump intralipid, which has scattering properties and will generate this OCTA signal at various speeds and in various configurations. So they created these microfluidic channels that sort of, not perfectly, but sort of mimic the vascular behavior in the eye with different sizes and different configurations. And they had a baseline configuration, one that showed dilation and one that had areas of ischemia. And at least if you look at the 3x3 scan, they aren't far off. There's no real tolerance here, but in the baseline case, they're measuring something that says 0.06 and we're measuring something that says 0.058. So they matched reasonably well, and also in the 3 different scenarios. The 6x6 was definitely worse because the resolution was worse. And that's something that, this is basically measuring the ability of your imaging system to pick up these signals that are going to be input into your density measurements. But what we wanted to do was test our actual algorithm. And in order to do that, we created digital phantoms. So this is basically, our own ones and zeros and grayscales that we put together to mimic a genuine cirrus image, but using things that we put there so we know that they're there. So we know what the ground truth is. So we actually just physically drew in the larger and medium-sized vessels because the actual configuration of them, we decided didn't matter very much. And we mimicked the microvasculature by basically doing these concentric circles with random cross-hatchings across them to sort of simulate the vascular network. And then you have to apply noise, both additive noise and multiplicative noise. And you can add this, and you have to broaden the vessels. So you can do all of these with different parameters. So you end up with a series. We ended up with, I think, 3,400 individual phantom scans that had configurations that we knew so that we could plot the density that came out of our algorithm versus the density that was put there. And this is showing a flow chart of this process where, we basically start with a template, create these medium, large, and micro vessel layers, add them together, downsample them, fuse them, create the noise and the broadening that is characteristic of the cirrus imaging, upsample them so that we can enter them into the algorithm, and then we get whatever the algorithm says is the correct answer, and then we have the ground truth that we already knew. And so I'm going to show you a couple examples rather than showing you the whole chart. We also simulated dropouts. You can see here that there are areas where we randomly applied loss into the eye, and we did this in increasing amounts as we went from the simulated visit 1 through a simulated visit 6. to see if, as the true density goes down, does our measured density go down? So this plot over here basically shows this. So as the disease worsens over this simulated time, you can see that the ground truth goes down. And in good news, our 3 millimeter by 3 millimeter measured density also goes down, and our 6 millimeter by 6 millimeter density also goes down. So none of these three things are the same as each other. The ground truth is not exactly recreated by our algorithm on the 3 by 3, and our algorithm applied to the 6 by 6 also differs significantly from the ground truth. However, as the numbers go down, as the density goes down, so do the measured numbers. And this is true for both the 3 by 3 and the 6 by 6 scan. So we can expect that as the eye gets worse, we will be able to detect that worsening. And that's the most important thing. So this is showing this effect for the vessel density in the 3 by 3 scan. Just to throw another example at you, we did the same thing on the 6 by 6 scans. And in this case, I'm showing perfusion density. Again, as the ground truth goes down, as you get more and more vessel dropouts, the measured perfusion density also goes down, and it goes down in both the 3 by 3 and the 6 by 6. So, we have a variety of pieces of evidence: diagnostic efficacy, repeatability and reproducibility, and a couple different phantom measurements demonstrating that angioplex metrics can be used to objectively characterize capillary closure, which is something that you would have instinctively thought by looking at normal eyes with early DR changes and proliferative diabetic retinopathy. But there's a lot of work you have to do to get there and be certain that you have achieved this sort of objective characterization. So there's a number of things I have not gotten to. In the future, of course, we're introducing larger and larger fields of view, and we're going to have to attack the quantification problem for those larger fields of view. And currently, we have also done all of the same activity, all of the diagnostic efficacy, all of the repeatability and reproducibility. The phantom studies have all been done for the ONH scans as well, which is looking at a different layer in a different position in the eye, but is still providing these objective measurements that have some correlation to disease. So I want to acknowledge all the people that have helped work on this over the years, including my colleagues at Carl Zeiss Meditech, and Ricky Wang's team at the University of Washington, Professor Cunhavas at i-POB, and our collaborators at Bascom Palmer Eye Institute, who have also been working on all of these topics with us.
Okay, so thank you very much, Mary. Mary cannot hear us actually because of some technical problems. We have no communication with her, but I will pass questions to her by email. Hopefully she can answer. And but this was really great talk, showing how the reality looks like in the industrialization process, especially to get approvals for the next stages of the implementation of new technology. So now we have last talk today. Also excellent speaker, Grażyna Palczewska. We have she's also very experienced in industrialization. She worked for a long time in a Philips company, and later as a director of medical device development at Polgenix ENC, and currently she's also employed by University of California, Irvine, and here at the Institute of International Center for Translational Eye Research. And she's recognized internationally for advancing two-photon excitation-based processes to study eye structure and function. And this is the one of the most promising ways of getting the functional information from human eye. So Grażyna, please, bandwidth is yours.
All right. Dear Maciej, thank you very much for such a generous introduction, and good afternoon. Hello, everybody, and thank you for staying so long. So, hello, and thank you, Maciej, for such a generous introduction. And I will talk today about the latest progress that we have made in advancing two-photon excitation processes to imaging of the retina, with, of course, the hope that we will be able to image human eye on the next slide, I will provide the introduction. First, I will talk about the endogenous fluorophores and how they are changing, and how is the imaging changing in health and diseased retina, and also how they are impacted by the therapy. And later I will present our latest data showing the 2-photon biopsy of retinal fluorophores, and also how we were able to reduce the power that is needed for imaging while maintaining the wonderful image quality. So eye, on the next slide, is the purpose of the eye is to connect, is to transmit the light, is to collect the light and then convert it to electrical signals. And those electrical signals are then interpreted by the brain, so we could see the world around us. The signal transduction, conversion of the light signals into the electrical, happens in the retina, which is the layer on the back of the eye, and it consists of multi-layer. It is a multi-layer structure with different specialized cells, and the conversion signal transduction occurs specifically in the photoreceptor cells, and more specifically in the outer segments of those photoreceptor cells. For this phototransduction process to occur, it needs to be supported by the processes that also occur in the retinal pigment epithelia or in the RPE. And this layer is extremely important for maintaining the health of the retina, as it supplies the nutrients to the retina, and it also participates in the regeneration of the visual pigment. Even though our most interest is in human eye, the vast knowledge that we learn about the processes that sustain vision comes from the studies in animals, and especially mice are of most importance, because right now with the genetic modification processes, we can create mice that mimic human diseases. On the next slide. And on the next slide, however, for the light to reach the retina, it needs to be transmitted through the cornea and through the lens, through the vitreous, through the aqueous, that all these layers need to be transparent, and thus create the window for us to image the back of the eye, such as here on the left is SLO imaging that provides the unfast imaging, and OCT that Mary was just beautifully introducing, showing the cross-section of the retina in the B-scan images and lately on the OCT angiography. However, these modalities tell us more, and its derivatives are fluorescent. However, most of the active vitamin derivatives have the absorption maximum at the ultraviolet range, like 330 nanometers for retinol, and the same for the retinal ester. For retinal is at 380 nanometers. Why they can absorb and emit. However, this absorption range is in the ultraviolet, which is poorly transmitted from the front of the eye, and furthermore, it is harmful to the retina. That's why we are working on the next one. We are working on the 2-photon excitation processes. Next slide, please. In the 2-photon excitation, 2 photons of lower energy do the job of the 1 photon with high energy. So thus, it is possible to excite the fluorophores, endogenous fluorophores in the retina, with the infrared light, which is safe, not only safe, but it also is being it is not so deformed by the different layers of the retina. However, for this 2-photon excitation process to occur, the 2 photon needs to meet at the same time and at the same place. Thus, higher light fluxes are needed to occur it. However, as we can see on the right slide, on the right panel here, we have additional benefit. The 2-photon, the infrared light, not only penetrates better through the eye, but it also, because it occurs, the 2-photon absorption effect occurs only in the focal volume, the 2-photon images, 2-photon excitation-based images are inherently free of the noise. And here I provided the equation, as we will use it later for explaining our path for improving the efficiency of the two-photon excitation. And we see that the two-photon excitation is mostly achievable when we use the pulsing lasers. And when we use the pulsing lasers, the fluorescence per fluorescence molecule is inversely proportional to the pulse duration, laser pulse duration, and the frequency. And on the next slide. So now with this technology, we are able to visualize endogenous fluorophores in the retina, in the RPE. And here we use the mice that are models of human genetic diseases. On the left panel, you see the RPE in the wild-type mice, and here you see the hexagonal shape of the RPE cells, and in the center of the cells, there are dark circles, and those are the nuclei. And very often, RPE cell has double nuclei, and the reason for this double nuclei structure is not fully understood. It could be related to the very high metabolic function that RPE is required to perform while sustaining the function of photoreceptors. The next panel, it's totally dark on the previous slide. Then the panel with the LRAD knockout is totally dark, and the reason for it that there is no vitamin A in that eye. That mouse is blind, and this is the model of one model of the Leber congenital amaurosis. The RPE65 knockout mice, on the other hand, opposite to the LRAD knockout mice, has the overaccumulation of the vitamin A derivative. This is retinol ester in this case, and the borders of the RPE cells are decorated with those particles, with granules that contain retinol esters. And the other model of the human diseases is the mouse knockout, which missing the ABCA4 and RDH genes. And here we have the totally different image where the fluorophores are uniformly distributed towards the RPE cell. Based on these images, one cannot exactly say what is the fluorophore responsible for the contrast here. Thus, with the laboratory animals, we were able to do the mass spectroscopy study coupled with HPLC, and we arrived at the conclusion that in the RPE65 knockout, those are retinol ester, and in the IBCA4 and RDH knockout, those mostly are all-trans retinal condensation products, such as A2E, like the product that is accumulated in the lipofuscin. And you have seen that the spectra from the pure compound are really independent of the excitation wavelength. However, emission spectra are dependent on the excitation wavelength, and this is mostly due because we have different types of fluorophores present in the eye. So on the next slide, I will also show images based on this two-photon excitation of the mouse and on mouse eye. And on the left-hand side, you have the mouse model that is mimicking many features of the Stargardt disease. And as we go from the top to the bottom, we go through this layer of the cells of the retinal cell, retina, and on the top is RPE, retinal pigment epithelium, outer nuclear layer, outer plexiform, on the bottom is ganglion cell layer. And on the right panel, if we click on the movie, then we will see in details that at the top is again the RPE, and then we see the details of the cone photoreceptors and with the inner segments coming here, and with the outer segment interdigitating with the RPE, which is the extremely important information here, as all this interchange between the photoreceptors and the RPE occurs in this area of the retina. And to achieve this image, to achieve this image and this detailed information about the photoreceptor cells, we have used the injection. We used the intravitreal injection of PNA, which is decorating the con cells conjugated with the fluorescein. And on the next slide, I'm showing how we applied this technique to tracing the presence of the drugs in the eye. And here we decorated PNA again with rhodamine. And here we also injected the mouse eye with the Avastin, which is the which is the drug against the age-related macular degeneration, late stage, the wet macular degeneration. Even though the drug is being sold and used quite widely in US and in the world, the mechanism of action of this drug is not fully understood. That's why it is extremely important that we are able to track it and see its depot in the eye, because it needs to work on the RPE, on the choroid. However, it's working by the injection in the vitreous. So these techniques are possible in the mouse, in the animal, however, not really possible in human. That's why we need to develop a different technique, and I will talk on the next slide about that, where we employ the fluorescence lifetime to provide a different contrast for the images. Next one. And here, when after two-photon excitation, molecule is excited and then emits the photon, that the timing of that emission of the photon is characteristic for the molecule. And by measuring fluorescence decay, the time when the fluorescence photons arrive as the function of time, we are able to determine what the compound is responsible for this fluorescence. And in this way, we should be able to transfer the images, like two-photon excitation images, intensity-based, into the two-photon excitation images of the tissue that are based on the fluorescence lifetime, which can tell us more about the distribution of different fluorophore and maybe about the transformation of those fluorophores or different form of vitamin A. So on the next slide, the instrument that is capable to do it, it needs to be equipped with the photodiode that detects the timing of the laser pulses and then transfer this timing to the detector, such the detector can start counting the photons after this initial pulse. And by counting the photons after the initial excitation pulse, we can create the decay function. However, using this decay function for characterizing every pixel in the image is a little bit complicated and not that informative. We would like to be able to capture all the information in one glance. And furthermore, to derive this information from the decay by using the deconvolution, by finding the different exponents, requires a lot of fluorescence photons. So the more efficient way of characterizing the fluorescence decay is using the so-called phasor transformation. And here the equation are. In this phasor transformation, the fluorescence decay in every pixel image is converted to the pixel on the so-called semicircle plot. And on the bottom, you see the panels from pure compounds. So the fluorescence is converted to the point characterized by the GIJ and SIJ coordinates. And we see that this point stays, doesn't matter about the excitation, stays very tightly on the circle. Retinal palmitate, which is a little bit more complicated compound, its phasor point lies inside the semicircle. And A2E is even more complicated, as its phasor changes both with the excitation, but it also changes with the concentration of the compound. So by using this transformation on the next, you will see how this is used for the imaging of the retina. And on the next slide, here are the images, the fluorescence lifetime-based images using the phasor transformation of the RPE65 knockout mice, which is the model of the LCA human diseases. Then in the middle row, it is ABCA4 RDH8 knockout and obtained with 850 nanometer excitation. And this is the mouse model that mimics Stargardt disease. And on the bottom is also the same mouse model, however, with different excitation wavelength, 730 nanometers. And it's very nice about the RPE65 knockout mice because the only fluorophore, the predominant fluorophore is the retinal esters, and we call it retinosomes. And it has very distinct point on the semicircle plot. On the other hand, when we use the 850 nanometer excitation, the only fluorophore we can excite is the A2E. And this one has a very well defined with 850 nanometer point here, phasor point in the right corner. And then, however, when we use the 730 nanometer excitation, we see the multitude of phasor points, and we see the group of points located where the retinosomes are, and we see the group of points that is located around the A2E. And then by selecting different colors for different region of this phasor plot, we can obtain a meadow-like looking map of the RPE. And this is the first time that we were able to confirm and show totally non-invasively, without the need for the mass spectroscopy or HPLC method, which are destructive, that subcellular distribution, and by this we could also be able to track how the changes of the subcellular distribution of different fluorophores in response to environmental insults. So on the next slide, we not only want to visualize that, but we also would like to be able to quantify it. So this is again this ABAC A4 RDH8 knockout mouse, which is the model of Stargardt disease. And on the left panel, by selecting points on the phasor plot below, I highlighted only the point in the image above. I am able to select the points that have the retinal ester characteristics. And then going from the left corner all the way to the violet corner here, we go through different compounds, and one could see that they have the distinctly different distribution in the RPE. Going back to the retinal esters, we did the comparison, and using image J, one can, for instance, quantify the area that is occupied by those retinosomes in the ABCA4 RDH8, and the same in the RPE65 knockout mouse, which is the only fluorophore. And because this is mouse eye, we compare the quantity of these compounds, and indeed we find the great agreement between the destructive measurements and the non-destructive measurements that is done by the two-photon excitation imaging with phasor analysis. Furthermore, we were intrigued by the situation that we not only have this distribution of the A2E at the points that we were expecting, but it's rather smeared like a line. And this is represented by the yellow, green, and then the violet color. And part of the reason of this is that we might have a different concentration of A2E. But the other reason is also that there are some other condensation product, as we could see that they are distinctly located as they are presented by the violet points. So this was very exciting for us. And on the next slide. So besides vitamin A, we have also other compounds in the eye, other molecules that have impact on the retinal health, as also on the ability to image. And one of them is melanin. And here, melanin, as we know, absorbs the light. So the way to characterize it, we use the section from the retina. And on the upper left panel, we have the section from the retina that is pigmented animal. And on the right panel, there is a section from the retina of the albino mouse. And by doing that, we have found the location of the phasor location of this melanin, of the melanin. And this allows us then to select, to find what is the best wavelength for the contrast to achieve in the pigmented eye. And by doing excitation with 730, 750, 780 nanometers, why we found out that actually the best imaging performance to image this active form of vitamin A, such as retinal ester, is by using 730 or 750 nanometers. Why at 780 nanometers, the melanin absorption is such and the emission that it obscures the signal from the retinosomes. And on the next slide, however, there are some problems with that melanin also, besides obscuring the signal. And if we run the movie here, we will see that if we click on the movie, then we will see that, okay, the movie doesn't play. So anyway, the melanin absorbs the light, and during this absorption of light, there is a damage to the retina. And the damage, the first to the naked eye, it looks like there are luminescent flashes coming from the melanin. So we had to do something to avoid these flashes. So then on the next slides, I will show you how we modify our system for increasing the efficiency of two-photon excitation while removing the problem, right, eliminating or mitigating the problem with melanin absorption. So can I have the next slide? And here is on the top of the system that is the device that we call pulse speaker. So if we imagine here the train of laser pulses coming into the pulse speaker, they come at 80 megahertz. By using this device, we can reject some of the pulses in such a way that only the certain pulses will be coming, only, let's say, every 10 pulse will be coming to the eye. And considering the equation that fluorescence is inversely proportional for the same laser power to pulse repetition, we can either increase the fluorescence or we can reduce the laser power and still be able to achieve the images. And on the next slide, by using this this technique, we have shown that with the higher pulse rate, we create damage in the retina, like in the upper row here. So here is the laser power and also the image, the brightness of the images. And the red arrows point to the location where there are those fluorescent flashes that are appearing in the choroid in this case. And the white arrows points to the bubbles which are formed in the retina as the results of overheating the retina. And when we use the lower pulse repetition frequency, we do not create this defect. In fact, we don't see any damage with the 8 megahertz and with 80 megahertz for the same laser power when the power escape before the 3.5 milliwatt for this system configuration. However, when we image with the 80 megahertz with this with the lower power, we don't get a very good images. So may we change to the next slide? And one thing that we check here, we were concerned whether this using different pulse rates will impact our fluorescence lifetime imaging, and we confirmed that it's not, that we get the same fluorescence lifetime signature whether we use higher or lower pulse repetition rate. And what I'm not showing you, we confirmed is the same with the spectral properties of the fluorophores, and the conclusion was the same. Thus, using this reduced pulse repetition frequency provided us with the tool for collection of fluorescence data with the low laser power and mitigating the retinal damage. And if we can have the next slide. So we were able to obtain the images in the live mice with the pigmented animals with low laser power of 1.5 milliwatt, 72 seconds. And that's a very short time that was needed to obtain these images. And here you see very clearly RPE cells with the retinosomes and nuclei inside these RPE cells as well, and with the very low exposure, which is several orders below what is prescribed by ANSI. And next slide. Thus, in the summary, I would like to tell you that by using imaging, two-photon excitation imaging with mice, we were able to show the phenotypes that we are able to show the distinct phenotypes of human diseases. We are able to track the drug distribution, and we can present the distribution of the fluorophores in the live animals. That is an extremely important step towards applying this technology to human. And on the next slide, I would like to thank our team that was intimately involved in obtaining this data, in developing the idea, and those into two different groups, Professor Krzysztof Palczewski and Professor Maciej Wojtkowski, and here Dr. Zhiqian Don, Jianie, Avery, Kuba, Patrick and Łukasz, and also I would like to thank Professor Enrico Graton, with whom we have collaborated on the phasor analysis of fluorescence lifetime. Thank you very much.
It was very clear, great talk with beautiful results, and actually very surprising, some of them, because when we take retina and extract it from pig eye, for example, the RPE is carbon black. So meaning that from the first glance, there must be like millions of different fluorophores that are completely mixed, and differentiation of these fluorophores is really very challenging. So we have one question concerning this, if these patterns that we see in phasors are reproducible for a higher number of animals. Is it something like unique, or it's more the relation between different parts of phasor is important?
So the phasors will be changing in relation to the quantity of the particular compound. So that's the information that we are after, that we would like to derive the proportions of which molecules are present, which types of vitamin A are present in the eye, and what is the proportion. So it is easy to use it on the mouse eye when you have the prevalent fluorophores or prevalent form of vitamin A. So this data could be then used as a guide to understand what we see in human disease.
Mm-hmm. And how specific are these mice knockouts that you used? Is this really very well controlled animal and experiment, or is like from one knockout to another it can be really completely different? How is it in practice?
So it takes some time to develop the mice models, and we very carefully characterize them using such a technique like PCR. So, and we perform this on the regular basis just to make sure that the mice stays purely. And some models, such as RPE65 knockout mouse, that exists at least for 10 years. And it was developed, and actually development of this mouse model established that protein, RPE, is the isomerase of the visual cycle, which is critical and indispensable for maintaining our vision. So that allowed the identification and confirmation, because these mice are blind, and these mice do not accumulate A2E, because there is a blockade of the visual cycle. On the other hand, the ABCA4 knockout and RDH knockout mice, these are characteristic of the Stargardt disease, and they lack two genes. So that development was a little bit longer. And then with the newer tools that are valuable, it would be a little bit faster, such as CRISPR, perhaps.
Mm-hmm. So another question is, how long the acquisition, what is the acquisition time per frame in vivo studies for FLIM analysis? That enables the phasor analysis.
Yes, the phasor analysis is this beautiful technique that allow us to characterize the retina with fewer photons that is needed by using the TCSPC with the traditional exponent finding. So typically it's about 60 seconds. It depends on the detail and on the type of fluorophores. So 60 seconds is enough to obtain this characterization in the mouse. In the pure compound, that could be less, as you have the entire image composed of the single type of molecule.
So there are other questions which can be combined. Have you investigated pulse width together with pulse rep rate, and what would be your dream laser source?
This is a very nice question. So yes, we investigated pulse width with the pulse. So the answer is easy. The first one, the dream laser source should have the pulse duration about 30 femtosecond, 30 to 20. When we go to the shorter pulse durations, we come up with the very wide bandwidth. And with the wide bandwidth, we lose detail of the information as we might be exciting too many fluorophores. And then you also not only use the information, but you also use the amount of power that is evaluable to characterize particular fluorophore.
And the last question is 3-photon feasible for your study? Would it help in anything?
Yes, we did some study with YAG lasers previously, and it dramatically improves the penetration through the retina. So you would have to go with maybe 1100, 1200 to be able to excite retinal esters or vitamin A products.
Mm-hmm.
That's but we have to keep in mind that with going from 2-photon to 3-photon excitation, the excitation cross sections are diminished appropriately. So we might have to pay for on one hand for increasing the penetration depth. We would have to pay with the increased power because we lost the 2-photon cross section. So this would be a lot of optimization that would have to happen there.
And there will also be some problem with water absorption, right? That there will be additional
and then the water
attenuation.
absorption. That's correct. Yes,
for
especially
in vivo
in the
studies.
light eye,
In
correct.
vivo, right?
Yep, or in vivo.
Okay, good. So thank you very much, Grażyna, for this beautiful talk. Actually, that concludes our last session today. And please stay with us tomorrow. So I would like to encourage you to stay with us because we will have another beautiful talks tomorrow with great speakers. So thank you very much for today, and have a good night.